Jupiter is our solar system's largest planet. It's more than twice the mass of all the other planets combined. Its swirling atmosphere moves in bands at different latitudes, and its great red spot is thought to be a perpetual storm. Recently, images from a new probe that has flown above Jupiter's poles reveal a completely different planet. The ancient Romans knew Jupiter as the celestial representation of the king of the gods. In 1610, Galileo, using his newly improved telescope, saw Jupiter's moons and could see they orbited the planet, evidence that not everything revolved around the Earth as the Church had declared. Though better telescopes improved our view of Jupiter, it was not until 1964 that Gary Flandreau, a graduate student working part-time at NASA's JPL, understood there was a way to get a clearer look at Jupiter. By plotting the positions of the outer planets, he realized that a rare alignment would enable a spacecraft, launched in 1977, to visit Jupiter, Saturn, Uranus, and Neptune. NASA jumped at the opportunity and began work on twin craft for what was then known as the Planetary Grand Tour. To limit any surprises, two basic spacecraft, known as Pioneer 10 and 11, were quickly built. They would go ahead of the Grand Tour missions to send back information about the environment. Pioneer 10 was launched toward Jupiter in March 1972. It was the first spacecraft to cross the asteroid belt that lay between Mars and Jupiter, and because it was the first probe on a trajectory that would take it out of the solar system, it carried a plaque identifying its origin. By December 1973, Pioneer 10 was sending back pictures of Jupiter clearer than anything that had been seen before. Approaching Jupiter, it encountered levels of ion radiation 10,000 times more intense than the radiation belts surrounding Earth. As the probe skimmed past the giant planet, it gained speed. Leaving Earth, Pioneer 10 was moving at 51,000 kilometers per hour. Departing Jupiter, it had more than doubled its speed. This gravitational slingshot effect made the Grand Tour possible. The Grand Tour craft, recently renamed Voyager 1 and 2, were due to be transferred to Cape Canaveral for launch integration when news of Jupiter's extreme radiation environment came through. The electron radiation at Jupiter had generated false commands within Pioneer 10. With the far more sophisticated Voyagers, this presented problems. Local supermarkets were stripped of their stocks of kitchen-grade aluminium foil, which was then used to shield critical cables. Without this last-minute alteration, electrical pressures of up to 40,000 volts would have been induced in the Voyager's subsystems as the craft passed Jupiter. Voyager 2 was launched in August 1977. Its trajectory meant that it could visit Jupiter, Saturn, Uranus, and Neptune. Voyager 1 left 16 days later. Its different, faster trajectory only allowed flybys of Jupiter and Saturn and various large moons. At the time, the Voyager spacecraft were the most sophisticated probes to be launched. Because they were to operate at huge distances from the Sun, solar panels could not be used as a power source. They were equipped with radioisotope thermoelectric generators which use the heat from the decay of plutonium-238 to generate power. As Voyager 1 approached Jupiter in January 1979, it began sending image sequences that showed a complex and dynamic planet. The planet's giant red spot was revealed as a vast rotating storm. In 1665, Giovanni Cassini described a permanent spot on Jupiter which was regularly observed into the 1700s. It was not until the late 1800s that Jupiter's spot was described as red, and it's uncertain whether the historic observations of Jupiter's spot refer to the same feature or a phenomenon that regularly manifests in Jupiter's atmosphere. Voyager 1 made its closest approach early in March 1979. As the probe neared Jupiter, the activity at NASA's Jet Propulsion Laboratory became intense. This was the nature of the Voyager's flyby missions. There were long, quiet cruise phases between the planets, followed by brief periods when the flow of information from the craft overwhelmed researchers. One of the biggest contributions made by the Voyagers was the transformation in our understanding of the Galilean moons. Previously just dots of light, Jupiter's 4 largest moons were each distinct and completely different. The first surprise was the inner moon Io. It's a sulfurous yellow in appearance, and one particular long-duration exposure revealed an odd plume. Rather than being a cold, dead world, the gravitational squeezing Io receives from its giant neighbor heats the moon's interior. The plume was a volcanic eruption, ejecting material hundreds of kilometers above the surface. In July 1979, 3 months after Voyager 1 had moved beyond Jupiter, Voyager 2 made its closest approach. It was able to examine different moons more closely than its twin. Europa was the next surprise. It is highly reflective and has the smoothest surface of any body in the solar system. Further observation revealed pressure ridges reminiscent of polar ice flows on Earth. Europa is a frozen world, with a vast ocean beneath a thick crust of ice. Like Io, it is heated from within by tidal flexing. As Voyager 2 continued towards Saturn, planetary researchers were left with large amounts of raw data about Jupiter still to be processed. The Voyager missions left us with a basic view of the Jovian system, but they had raised more questions than they were able to answer. It would be more than 10 years before Jupiter received another visitor from Earth.
Ignition and liftoff of Discovery and the Ulysses spacecraft bound for the polar regions of the Sun.
In October 1990, the Space Shuttle Discovery lifted the European Ulysses spacecraft to low Earth orbit. From there, it was boosted on a mission to observe the Sun, but first, it would pass Jupiter. All the planets orbit the Sun in the same direction, in roughly the same plane. This is called the ecliptic, and it developed from the spinning disk of dust and gas that formed our solar system. The designers of the Ulysses spacecraft wanted to see the Sun from an orbit above its poles. Jupiter's extreme gravitation was used to bend the probe's flight path out of the ecliptic so it could make north-south orbits of the Sun. Ulysses was not the only probe to take advantage of Jupiter's gravity. Both the Cassini probe to Saturn, launched in 1997, and the New Horizons probe to Pluto, launched in 2006, were able to reduce their flight times by years with Jupiter flybys. These probes were able to make meaningful observations while passing the giant planet. clean rooms of the Jet Propulsion Laboratory, a new probe was taking shape. Galileo would be the first spacecraft to go into orbit around Jupiter. Its 4.8-meter antenna was folded like an umbrella, only to be deployed when safely on the way to Jupiter. Originally scheduled to launch in 1986, it sat in storage for years after the Space Shuttle Challenger exploded.
10, 9.
It launched aboard Space Shuttle Atlantis in October 1989.
4, 3, 2, 1. We have ignition and liftoff of Atlantis and the Galileo spacecraft bound for Jupiter.
New rules governing shuttle launches meant a change in the booster to push Galileo out of Earth orbit. The less powerful solid fuel upper stage, now stipulated, sent Galileo toward Venus for a gravity assist. The new flight path meant Galileo was traveling to a hotter part of the solar system. It was decided to keep the heat-sensitive antenna furled until after the spacecraft looped back past Earth. Galileo made 2 close passes of Earth, each time gaining more speed. Its first pass was in December 1990, more than a year after its launch. A further year on, when it passed Earth again, the high-gain antenna was only partially open. After months of trying different techniques to deploy the antenna, mission engineers concluded that long periods in storage had caused lubricant at the tips of the antenna's ribs to dissipate. Researchers would rely on Galileo's smaller antenna, with data delivered at slower rates. During the cruise to Jupiter, Galileo encountered several asteroids. This is Ida, the first asteroid we've learnt of with its own moon, Dactyl. In July 1995, while it was still 6 months away from its closest encounter with Jupiter, Galileo ejected a small probe designed to enter the atmosphere and sample its chemical composition. The probe lasted for an hour in Jupiter's atmosphere. The data was relayed to Galileo and recorded for subsequent transmission back to Earth. Its analysis revealed hardly any water vapor, which was unexpected, and other elements, particularly helium, were detected at far lower levels than predicted. The probe experienced areas of extreme heat and cold, suggesting heat is being released from the planet's interior. Slightly more than an hour after transmission from the probe ceased, Galileo began its orbit insertion burn. Its engine had to operate for 49 minutes to put it into a highly elliptical equatorial orbit. But this orbit would be altered with another burn at its high point. Mission designers were acutely aware of the high radiation environment, and the second burn would lift Galileo above the extreme radiation at its closest approach. Galileo's initial orbit eventually delivered a close approach to Ganymede, Jupiter's largest moon. During this orbit, engineers were trying to understand damage to the spacecraft's vital tape recorder. Without its high-gain antenna, the recorder was essential for slow replay of data recorded during the brief, close encounters. It had been stuck in rewind for 15 hours, and tape had been degraded. Light-emitting diodes, key elements in the recorder's control system, had acquired radiation defects. The second orbit also passed Ganymede. Galileo discovered it's the only moon in the solar system with a significant magnetic field. It also has an ocean sandwiched between 2 layers of ice. Galileo's orbits would be slightly varied so that it could make close approaches to different Jovian moons. But the equatorial orbits needed to reach the moons also took the craft through hotspots in Jupiter's radiation belts. With the observations made by the Voyagers, the moon Europa was of particular interest to the Galileo team. Data from several instruments agreed that a salty ocean exists beneath Europa's surface ice. Later examination of the Galileo datasets revealed plasma wave and magnetic field information, showing that plumes of water vapor were erupting from cracks in the surface. Europa has more water than Earth, which makes it a possible home to life. Io was already known to have volcanic activity, but Galileo saw tides in the Moon's solid surface of more than 100 meters. The temperatures generated by this gravitational distortion of Io make its numerous volcanoes hotter than anything found on Earth. During its 8 years at Jupiter, Galileo completed 35 orbits, filling out our limited picture of the Jovian system. This was never an easy mission. Galileo was a robust spacecraft, but the radiation environment stressed all the subsystems, and engineers were constantly having to find workarounds for the frequent breakdowns Galileo suffered. Instruments showed increased noise when near Jupiter, and current leakages caused by radiation led to several resets of the onboard computer, with crucial loss of data. Software changes enabled the computer to recognize these resets and to recover by itself. Information learned would lead to changes in the way the next Jupiter spacecraft was designed.
5, 4, 3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter.
In August 2011, Juno began a journey to Jupiter that would last almost 5 years. Its mission parameters would be very different to Galileo's. It would ignore the moons and focus exclusively on Jupiter.
Chamber pressures have plateaued.
Spacecraft design saw crucial electronics shielded within a thick titanium vault, and rather than a plutonium power source, Juno would rely on solar panels. The Sun's intensity at Jupiter is roughly 5% of what it is at Earth, so the panels are huge. A shortage in stocks of plutonium-238 led to the change in power sources. Juno followed a looping orbit that took it beyond Mars before swooping back to Earth for a gravitational boost that added 14,000 kilometers per hour to its velocity, sending it on to Jupiter. Juno approached Jupiter on a path that took it above the planet's north pole. It was destined for a north-south orbit. This would see it pass beneath the severest sections of the planet's radiation belts that extend out from Jupiter's equator. 4 days before its closest approach, Mission Control sent a command that initiated the craft's autopilot. On July the 4th, 2016, Juno began an engine burn that would insert it into a 53-day orbit. 48 minutes later, Mission Control at JPL received tones verifying that Juno had started its deceleration maneuver. It was a tense 35-minute wait from the system's engineers before confirmation came through that Juno had performed exactly as intended. For the Juno scientists and engineers, it was a relief that things were going to plan.
Roger, so move, Juno.
Juno is equipped with a suite of instruments capable of penetrating Jupiter's thick cloud. The polar orbit allows Juno to compile a three-dimensional map of the upper atmosphere, building a picture of the entire planet as it rotates. The images of Jupiter from this new perspective appeared to come from a different planet. Researchers were stunned. It was planned that Juno would only make 2 53-day orbits and then change to a series of 14-day orbits that would speed up the sampling rate. The spacecraft's main engine is fueled by hydrazine and nitrogen tetroxide, which ignite spontaneously when mixed. The propellant and oxidizer are forced out by a bladder of expanding helium. As Juno was finishing its second orbit, the helium valves were not responding correctly, so it was decided to maintain the original orbit. A mission extension has been granted to allow for the longer orbits Juno continues to follow. Within a day of the helium valve problem, Juno went into safe mode. All instruments went offline and data was lost. It appeared to be similar to the difficulties experienced by Galileo, but engineers traced the issue to a data transfer problem from one specific instrument, and the spacecraft remains healthy. Jupiter's axis is tilted at only 3 degrees, making even an oblique view of the poles near impossible until Juno arrived. When viewed in the infrared, researchers saw a complex arrangement of storms at both the poles. At the North Pole, a central vortex is surrounded by 8 anticyclones. At the South Pole, 5 anticyclones surround the central storm. Scientists do not understand why the storms, all rotating in the same direction, do not obliterate each other. On its 7th close pass of Jupiter, Juno flew directly over the giant red spot. Its microwave radiometer was able to map the heat distributions at varying levels down to 350 kilometers. The red spot is a giant storm, and Juno was able to see much higher temperatures at the deepest levels they could penetrate. With no geographic features, as on Earth, there is nothing on Jupiter against which storms can dissipate. The Great Red Spot remains firmly 22 degrees below the equator, yet it appears to have drifted around the planet at least 10 times since reliable observations began. Jupiter's magnetosphere is huge. It traps charged particles in bands stretching out to vast distances. This gives sensitive electronics on orbiting spacecraft like Juno big problems. It was assumed that Jupiter's magnetosphere was generated, like Earth's, by dynamo action, the convective movement of an electrically conductive fluid deep within. So far, results from Juno suggest that this is not the case. The lumpy nature of Jupiter's magnetic field points to an atmospheric source. The giant auroras at the poles also seem to come from a different mechanism than here on Earth. By focusing on the composition of the gas giant, researchers are hoping to gather clues about conditions at the formation of the solar system. While the Earth has been continuously changed by tectonic forces, it is thought that Jupiter remains very similar in composition to the cloud of gas and dust from which the solar system was formed. At the end of its mission, Juno will be sent on a collision course with Jupiter to avoid any possible contamination of the delicate moons. The next mission to the Jovian system will focus on Europa, as the most likely place after Earth to harbor some form of life. Known as Europa Clipper, it's scheduled to launch in 2022. Like Juno, it will be solar-powered, and its elliptical orbit of Jupiter will see it fly over Europa every 2 weeks. Early concepts for the mission called for the inclusion of a lander, but this idea was soon rejected as premature because more needs to be learned about the surface of the icy moon. Though Europa's ice crust is thought to be at least 19 kilometers thick, accurate measurements need to be made. If thin areas can be found, then future missions may be able to access the ocean that lies beneath. Concepts for under-ice explorers are in development, and we can expect other missions to focus on other moons. As the largest planet, Jupiter's influence on the rest of the solar system is profound. It has more than twice the mass of every other planet combined. all other planets' orbits are affected by Jupiter's gravitation. There is still much to learn about Jupiter. The ringed planet Saturn. More than 100 times the mass of Earth, its metallic core lies beneath 80,000 kilometers of liquid hydrogen and helium. It's called a gas giant. Saturn is orbited by at least 62 moons, each unique, some with complex and dynamic environments. Our only detailed examination of the Saturnian system ended in 2017, when the Cassini probe was intentionally crashed into the planet's dense atmosphere to guard against accidental contamination of the moons. Viewed from Earth, Saturn's rings are visible, but not in any detail. They were thought to be solid until mathematical analysis suggested they were orbiting particles. But how did they get there? And why was Saturn alone in having rings? In the early days of space research, Saturn was just too far away. Conventional rockets could only just reach Mars. In 1964, NASA realized that a space probe launched in 1977 could take advantage of a rare alignment of the outer planets to fly past all the gas giants. Using gravitational assistance from the planets, it would just be possible with the technology of the day. An ambitious new mission began to take shape. It was dubbed the Grand Tour. Two probes that were far in advance of anything yet attempted would be part of the Mariner series. Because no spacecraft had been sent beyond Mars, mission planners felt it would be wise to send two rudimentary advanced probes to Jupiter and Saturn to test the deep space environment. Researchers didn't know if it was even possible to cross the asteroid belt between Mars and Jupiter. In 1972, Pioneer 10 was launched towards Jupiter, and the following year, a twin, Pioneer 11, was sent to Saturn. Both craft passed by Jupiter and discovered that the electron radiation there was 10,000 times as strong as at Earth. This was a surprise to engineers at NASA, who had to modify the more sophisticated craft they were preparing for the Grand Tour. The probes, being built at NASA's Jet Propulsion Laboratory, were part of a program known as Mariner Jupiter-Saturn, but this was soon changed to the Voyager program. They were launched 16 days apart in late 1977, while Pioneer 10 was heading toward interstellar space, and Pioneer 11 was still 2 years away from Saturn. In 1979, as Pioneer 11 approached the ringed planet, it began sending back pictures far clearer than anything seen before. A new ring, the F ring, was observed for the first time. The craft flew by Saturn, passing beneath the rings. Mission planners were uncertain how broadly the ring particles spread. If there was a threat to the spacecraft, they were prepared to sacrifice Pioneer 11 to get a clear idea of the environment they would encounter with the following Voyager craft. The probe passed the rings safely and continued beyond Saturn into interstellar space. NASA received its last communication from the probe on the 24th of November 1995. The following Voyager 1 and 2 probes were very robust, designed to survive for a very long journey and with far greater technical capacity than the Pioneers. In late 1980, Voyager 1 approached Saturn. Although its high-resolution polarimeter had failed, it was still able to see a new ring called the G ring, orbiting 100,000 kilometers above Saturn's cloud tops. For the first time, researchers could see how the rings moved. Uneven features within the rings were called spokes. They're transient and are thought to be particles lifted by an electrostatic charge. After such a long preparation, information was now coming into JPL at such a rapid rate that the planetary scientists were overwhelmed. Saturn's moons were of great interest. Voyager 1's path had been chosen because it would take it close to Titan, the solar system's second largest moon, and the only one to hold an atmosphere. But the images were disappointing because the thick atmosphere of methane and nitrogen was impenetrable. Voyager 1 now looped up above the solar system on a trajectory that would take it to interstellar space. As it looked back at Saturn, it captured one last image from a unique angle. It was almost 10 months before Voyager 2 neared Saturn. Its different path meant that it could continue on to Uranus and then to Neptune. Its high-definition camera was still working, and planetary researchers were expecting detailed pictures of the rings. They were not disappointed. The varying densities and spacing within the rings was more complex than anyone had expected. The rings are named for letters of the alphabet in the order that they were discovered. It became apparent that the rings had changed in the time since Voyager 1 had seen them. Though they stretched from 7,000 to 80,000 kilometers above Saturn's equator, their thickness is on average just 30 meters. The spacecraft also returned pictures of the moon Enceladus. Its cracked, uncratered surface was made of ice, below which is an ocean. Ultimately, Voyager 2 left Saturn. Unable to go into orbit, it sped on toward Uranus. It would be 23 years before another probe visited.
And liftoff of the Cassini spacecraft on a 30-mile trek to Saturn.
Launched in 1997, Cassini was a collaboration between NASA, the European Space Agency, and the Italian Space Agency. It would take more than 6 years to reach Saturn. Cassini was the biggest, most complex interplanetary spacecraft yet devised. Its 12 different instruments each had a dedicated team of research specialists on Earth to interpret the data it sent back. Its high-gain antenna was used for high-speed data relay back to Earth, but in what's called a ram maneuver, it was sometimes used as a shield to protect the spacecraft from debris impact, especially when crossing the plane of Saturn's rings. On the 1st of July 2004, it fired its engine to go into orbit around Saturn. It was designed not to fail. Beside its main engine was a backup in case the primary engine did fail. It had 16 monopropellant thrusters, 8 prime, and 8 more, also as backups. In mission control at the Jet Propulsion Laboratory, the engineers could not know what was going on. The time delay and Cassini's disappearance behind Saturn meant that much of the telemetry was recorded for later replay back to Earth. The engine burn lasted for 106 minutes. Cassini was the first probe to employ a solid-state recorder, unlike the earlier Voyager craft that registered data on a mechanical tape recorder. Cassini's first orbit followed a highly elliptical path that would take it out past the moon Titan. This was important for two reasons. Its gravity would be necessary in modifying Cassini's course, so Saturn and its other moons could be observed from different perspectives. Secondly, Titan, with its dense atmosphere, was targeted as an area of major interest for the Cassini team. The European Space Agency had built a small craft called Huygens, attached to the side of Cassini. On its second approach to Titan, the Huygens probe was released. It was equipped with a heat shield, a parachute, and enough battery power to last for several weeks. Over a 20-day period, Huygens drifted for 4 million kilometers. It would transmit data back to the orbiting Cassini, which would later relay it to Earth. 3 days after separation, Cassini made a course correction that would prevent it colliding with Titan. As Huygens reached Titan's atmosphere, Cassini was coming around for its third close approach of the moon, ready to receive signals from the lander. While it drifted to the surface of Titan, Huygens sampled the atmosphere and recorded images of the landscape. Pictures from beneath the clouds revealed low hills and channels cut by flowing liquid. There were few impact craters, and those that existed were heavily eroded. It was the first landing on a body in the outer solar system. Images from the surface showed weathered rocks made of water ice. What surprised everybody was that Titan is a geologically active world, where liquid ethane and methane, rather than water, have carved the features. As Cassini continued looping out around Titan, it used radar to map the moon's surface, confirming the widespread distribution of hydrocarbon lakes. The probe discovered that rain fell on Titan, but it was a mixture of liquid ethane and methane. The moon has weather and other erosive forces similar to Earth, but the chemistry is radically different. The small moon Enceladus drew attention to itself as the whitest, most reflective body in the solar system. Its surface shows cratering in the north, but the south has giant cracks known as tiger stripes. On Cassini's first loop past Enceladus, the magnetometer team noticed an odd deflection of Saturn's magnetic field, as though the small moon had an atmosphere. During its second pass, the team noticed the same phenomenon. They asked for the next traverse of Enceladus to pass much closer, so Cassini's course was modified to fly just 175 kilometers above the icy moon. The probe passed through a plume of water vapor emanating from the tiger stripes. It contained common salt. In all, Cassini made 24 swoops past Enceladus, with the closest approach flying just 25 kilometers above the surface. Each one of the probe's instruments gathered different evidence about the jets of water expelled through the cracks in the moon's south. On Mars, rovers have been combing the surface looking for traces of life, but Enceladus was flaunting remarkable signs. Gravitational analysis revealed a liquid ocean beneath the ice, and infrared detectors saw heat emanating from the cracks. As well as salt, the science team discovered traces of silica that can only dissolve in hot water. Hydrogen and organic compounds were also detected.
We know from Cassini that Enceladus has a global ocean, so you have water. We also know that there are organics coming out because they've been directly measured, both in the gas and in the particles. We also know there's a source of energy. The South Pole was hotter than the rest of Enceladus. And then we found evidence that deep inside, there are hydrothermal vents on the seafloor of Enceladus. So these hydrothermal vents would supply the heat and the nutrients that could possibly support life.
With a diameter of 500 kilometers, Enceladus is just too small to sustain a hot core via radioactive decay. Gravitational squeezing by Saturn explains some of the heating, but the source of the high temperatures detected remains a mystery.
But not only is there liquid water underneath the surface, but there's organic material, there's a heat source. And you know, when people get excited about the potential for life elsewhere in the solar system, there are four things that you need. You need a heat source, you need liquid water, you need organic material, and you need those three things to be stable over some period of time so that life could potentially form. At Enceladus, we've got three. We're not sure about the stability over time yet.
In the Earth's deep oceans, hydrothermal vents provide the warmth and nutrition to support life. They may even have been important for the origins of life. Planetary biologists are speculating that the environment in the oceans of Enceladus may be the most likely place in the solar system to find some sort of extraterrestrial life. It took a while for Cassini to be in a position where backlighting from the sun allowed the imaging team to capture pictures of the plumes. Using a similar technique, the imaging team took this picture with Saturn directly between Cassini and the Sun. It reveals Saturn's E-ring, the hazy outermost ring that is usually very difficult to see. The E-ring is a result of the plumes from Enceladus and is constantly replenished by the saltwater eruptions. Saying that Saturn has 62 moons is misleading. Each particle within the ring system could be regarded as a moon. There are the inner large moons and the outer large moons. There are the shepherds that shape the rings. There are co-orbitals that exchange orbits. And there are even moons that orbit other moons. All are unique. During the Voyager missions, interest in the moons came as something of an afterthought, but for Cassini, close examination of the moons was planned from the beginning. Iapetus orbits Saturn beyond Titan. It was first observed in 1671 by Giovanni Cassini. He could see it as a dot of light to the west of Saturn, but could not see it when it should have been to the east. Iapetus has one bright face and one dark one. Because the moon is tidally locked to Saturn, it is always the dark face that leads as it orbits. One theory suggests that it sweeps up debris that spews from Phoebe, a more distant moon. Another feature of Iapetus has scientists baffled. A ridge along the equator stretches more than halfway around the moon. It's twice as high as Earth's tallest mountain. With Iapetus being just 1,500 kilometers across, the ridge gives Iapetus the appearance of a walnut. Very accurately directed bursts from Cassini's main engine allowed mission engineers to modify the probe's looping orbits so mission specialists could focus on various moons, different areas of the ring system, or different parts of Saturn itself. With gravitational assistance from the moons, particularly Titan, mission control were able to conserve fuel. The Cassini probe performed so well it received 2 mission extensions, but the fuel could not last forever. Planners had scheduled the most hazardous part of Cassini's mission for its final year at Saturn. Late in 2016, Cassini began a series of polar orbits that would take it close to the outer edge of the rings. In what mission specialists called grazing on the rings, the craft's mass spectrometer and its cosmic dust analyzer would sample particles and gases as it crossed the ring plane. In orbit 251, its first pass above Saturn's North Pole, it recorded the peculiar hexagonal storm that was first hinted at by the Voyagers. The storm, more than twice the diameter of Earth, maintains its hexagonal shape, but its color changed with the advance of summer. At its center is a cyclone, shown here in false color, with red indicating lower cloud and green higher cloud. Winds at its edge blow at 540 kilometers per hour. One part of Cassini's dual-technique magnetometer had stopped working early in the mission. Without it, the craft had to do roll maneuvers from time to time to calibrate the instrument. The spacecraft would make 20 ring-grazing orbits, with the work of its instruments mapped out to the second. As the Sun was almost directly behind the rings, Cassini looked for dust clouds. Something is reducing ring particles to fine powder. Cassini made a number of radio occultation observations. With the rings between the spacecraft and Earth, 3 radio signals of differing wavelengths were transmitted simultaneously, allowing the radio science team to build a profile of the ring particles. This false color image of the A ring, the outermost of the large bright rings, shows red for particles larger than 5 centimeters across. Green denotes particles smaller than 5 centimeters, with blue for particles smaller than 1 centimeter. The complex gravitational interaction between Saturn, its rings and its moons leads to gaps in very particular places. Before Cassini arrived, only 18 moons were known. That number has grown to 62. Prometheus acts as a shepherding moon, limiting the inner edge of Saturn's F ring. Along with Pandora, which orbits outside the F ring, the 2 moons keep the ring narrowly confined. In April 2017, Cassini's orbit was changed for the final phase of its mission. The probe would now loop inside the rings. Though it would ultimately mean burning up in Saturn's atmosphere, the information gathered from such close proximity to Saturn and its rings would give a fuller picture of the gas giant. It was decided that intentionally destroying Cassini was preferable to letting it drift without fuel, possibly contaminating one of the moons. Cassini's sensors began picking up a stream of ring particles raining down upon Saturn. A continuous shower of ice and dust particles are dragged toward the planet's equator by gravity, or at higher latitudes, charged ring particles spiral in along magnetic field lines. Every second, 10,000 kilograms of ring rain falls to the surface. At this rate, the rings will be completely gone in 100 million years. Researchers were surprised to discover an electric current flowing between the inner D ring and the upper atmosphere. Toward the end of Cassini's close passes of Saturn, the spacecraft began catching the upper edge of the atmosphere. All information had been retrieved from the recorders. Data now was transmitted directly back to Earth, but it relied on the spacecraft's thrusters to stop Cassini from tumbling, keeping its high-gain antenna pointed accurately. The probe's final work was sampling the atmosphere, and measuring the offset of Saturn's magnetic axis.
This is ACS-1. We just had transition to high rate mode.
In mission control, there was no more control. The engineers could just monitor the signals sent from Saturn 84 minutes previously.
The signal from the spacecraft is gone, and within the next 45 seconds, so will be the spacecraft.
It will take years to process the data gained from Cassini. As yet, there are no future missions to Saturn scheduled. Mars, our planetary neighbor. It's very cold and dry, and its weak gravity only holds a thin atmosphere. As probes started to visit the red planet, we gained a more accurate view of the surface, and scientists began to wonder. Mars had once been much warmer. It had rivers, and in its early years might have sustained life. A succession of new techniques have been deployed trying to unlock the secrets of the red planet. And while our knowledge of the Martian geology, its atmosphere, and its weather has grown immensely, each new mission to Mars raises more questions than it answers. We still don't know if Mars has, at some time, been a home to life. In 1877, astronomer Giovanni Schiaparelli made what he thought was the most accurate map of Mars yet drawn. On it, he showed canals. In the early 20th century, American astronomer Percival Lowell was convinced the canals were signs of a civilization existing on the red planet. So began the search for life on Mars. In 1962, the Soviet Union sent the first probe, the Mars M1, on a flyby mission. It was an audacious project, and it failed. The first of many failures by both the Soviet Union and the United States. Cold War rivalry provided the motivation for these early missions. In 1971, NASA sent Mariner 9 to Mars. It was the first probe to orbit another planet, but scientists discovered that Mars was enveloped in a planetary dust storm. On-orbit photography revealed little more than a red cloud. Soon, Mariner 9 was joined by two Soviet orbiters, both equipped with landers. The Mars 2 lander crashed, but the Mars 3 lander made it to the surface intact. It returned one garbled image and then stopped functioning. Mars now had 3 orbiting spacecraft, all looking at a dusty, featureless planet. The two Soviet probes were identical, but the American probe had one key design difference. While the Soviet orbiters began photographing the planet following predetermined schedules, NASA were able to command Mariner 9 to wait, in hope that the dust would eventually settle. It took months for the atmosphere to clear, but when it did, Mariner 9 saw 3 craters protruding above the dust. They were the tops of giant volcanoes on what was called the Tharsis Plateau. Soon more complex geological features began to emerge. In places, the surface was cratered, suggesting the tectonic forces that constantly renew the Earth's surface were absent on Mars. Volcanic activity that built the solar system's largest volcanoes had stopped billions of years ago. This enabled NASA scientists to compile an accurate global map of Mars and to decide upon landing sites for the Viking probes that followed in 1976. Viking 1 and 2 were identical orbiters, with landers that both made successful landings on the surface. Both returned pictures of the Martian landscape. The primary objective of the Viking program was to find signatures of life. But researchers now feel the 3 experiments tasked with carrying out the analysis had limitations. As researchers on Earth began looking for traces of life in extreme environments, they began to rethink where life on Mars might survive. Yet the consensus at the time was that Mars was sterile, and the idea of life on Mars died. After a 20-year hiatus in Mars research, Mars Global Surveyor went into orbit in 1996. The pictures it relayed back were clearer than anything yet seen from the Red Planet. Although most Mars orbiters had been tasked with mapping the planet's surface, this was different. The high-resolution images that the Mars Global Surveyor sent back revealed rivers and even river deltas, but the occasional impact crater suggested that nothing has flowed in these systems for millions of years. In July 1997, another probe arrived. The Mars Pathfinder was one of a new breed of missions being pushed by NASA's new administrator under the guiding philosophy of faster, better, cheaper. The idea was to cut development times, cut budgets, and although the risk of failure would rise, the reduced price tag could mean more missions. Pathfinder would land a small rover on the surface. To do this, it used radically new airbag technology. The technique drew more from automotive safety systems than from previous space missions. The landing site, in Mars' northern hemisphere known as Ares Vallis, is one of the planet's rockiest areas. Yet it was thought to be a safe area to land. The broad array of different rock types are believed to have been deposited during an ancient flood. The new landing technique worked perfectly and served as a proof of concept that would be used on future missions. Pathfinder consisted of a base station equipped with 3 solar panels that unfolded like petals. There were sensors to measure atmospheric pressure, air temperature, and wind speed, as well as a transmitter to communicate with Earth. In addition, Pathfinder acted as a base station for the Sojourner rover that explored the surrounding area. Sojourner was fitted with cameras and an alpha particle X-ray spectrometer. It was the first mission to have its own website. The rover returned thousands of images and important detail about the atmosphere and geology, and its popularity guaranteed more Mars missions. On the morning of April 7th, 2001, another Mars orbiter was launched. Mars Odyssey was equipped with 3 primary instruments, and it had the ability to act as a relay satellite between future surface missions to the Red Planet and Earth. On its arrival at Mars, it used a new technique to go into orbit. After firing a relatively brief pulse of its engine, Mars Odyssey went into a highly elliptical orbit that, at its closest approach, had it skimming the planet's thin upper atmosphere. Called aerobraking, this technique allowed the craft to circularize its orbit over a period of 3 months, and it saved around 200 kilograms of fuel. The probe is still in operation today, breaking all records as the longest-serving Mars mission. In December 2003, a new player arrived at Mars. The European Space Agency, using a Russian launcher, had sent Mars Express, its first planetary explorer. It was equipped with a lander known as Beagle. Though all contact was lost with the lander, Mars Express continues to return valuable data. The mission has been granted several extensions, the latest till 2020. Equipped with a high-resolution stereo camera, the probe returned unique 3D views of the planet's surface. The orbiter determined that the polar ice caps contain a blend of frozen CO2 and water ice. In the atmosphere, Mars Express detected first methane and then ammonia. Both gases deteriorate rapidly in sunlight, so there must be sources on Mars continually producing them. Methane and ammonia can rarely be made inorganically, but they're generally associated with life. 1 month after Mars Express went into orbit, a NASA lander arrived at Mars, followed 3 weeks later by a second identical craft. They were the Mars exploration rovers called Spirit and Opportunity. Spirit, the first to land, was targeted at the Gusev crater. Opportunity would land at the Meridiani planum on the opposite side of Mars. Though they were much heavier than their Pathfinder predecessor, they used the same bounce landing technique. Both landings were successful and on target. After the craft had righted itself, it detached from the lander and began autonomously unfolding its solar panels and camera mast. While this was happening, the team back at the Jet Propulsion Laboratory waited. Signals confirming the craft's safe arrival took 15 minutes to travel back to Earth. Many of these people had invested years of their lives in this project, and the real mission had only just commenced. Both rovers were designed to operate for 90 Mars days. A solar day on Mars is about 40 minutes longer than an Earth day. And to avoid confusion, the science team operating the rovers refer to a Martian day as a sol. Mission designers, knowing about the dust storms on Mars, felt that the solar panels on the two rovers would eventually be blocked with dirt and stop functioning. But it became clear that the winds on Mars were clearing the panels. Soon, NASA announced that Opportunity had found evidence confirming liquid water had once flowed on Mars. There were pictures from the Meridiani planum of stratified patterns in the rock suggesting sedimentation. The distribution of chlorine and bromine at the site were clues to the areas past as the shore of a salty sea. In April 2004, NASA announced it would extend the rover's missions from 3 to 8 months. It would be the first of many such mission extensions. The rovers were equipped with an abrasion tool to grind away a portion of a rock's surface for a more detailed, uncontaminated analysis of geological samples. This was first done by Spirit at a rock named Adirondack at Gusev crater. It was a first in planetary geology. Researchers agonized before using the tool because of the drain it makes on the rover's energy budget. The rock was made of olivine, pyroxene, and magnetite, making it very similar to volcanic basalt on Earth. When Spirit's right front wheel stopped working, engineers used a duplicate rover to devise a reversing technique that enabled the rover to drag its frozen wheel. This left a furrow behind in the soil, which presented a new area of research for the science team. White or yellow deposits seen within the furrow were various types of salts that only form in the presence of hot water. On Earth, hot water provides an environment in which microbes can thrive. Spirit limped on for another 3 years before it became stuck in loose sand. Again, the engineers began working with a replica which they placed in an identical situation. When nothing was able to free the rover, it was declared a stationary research platform. Further attempts were made to position the rover so its solar panels could operate more effectively, but even this was not possible. The last communication from Spirit was in March 2010. Opportunity lasted until June 2018, when dust clogged its solar panels. In March 2006, NASA's Mars Reconnaissance Orbiter arrived at Mars and began the now routine business of aerobraking. Though this procedure took roughly 6 months, the saving in fuel will see the craft functioning at Mars into the 2030s. One of the primary functions of the new orbiter is as a communications relay station. Its 3-meter antenna transmitting in the ultra-high frequency band enables very high data rates. By November 2013, it had tripled the amount of data sent to Earth by all the other NASA missions combined. Its high-resolution camera began revealing the surface of Mars in the finest detail. These are active falling dunes in East Coprates Chasma. The polar region, free of the seasonal dry ice, again surrounded by dunes. In the southern hemisphere, pits in the residual cap of carbon dioxide. The poles of Mars were now attracting keen interest. Follow the water had become NASA's catch cry. The Phoenix lander was targeted at the northern polar region to follow up on information from Mars Odyssey suggesting frozen water lay beneath the surface near the poles. Because imaging had revealed the region to be unvarying, a rover was deemed unnecessary. The lander had been designed to use a parachute to decelerate, with rocket thrusters to deliver the craft to the surface, unlike NASA's previous 3 rovers, which had bounced. This decision proved controversial, as one strand of research suggested the rocket fuel would contaminate the very area that the lander was tasked with analyzing. The craft waited 15 minutes to allow any dust to settle before it deployed its solar panels. Phoenix had landed during the early spring in Mars's northern hemisphere, so the solar panels would receive plenty of light for the planned 90-day mission. As well as its camera mast, Phoenix was equipped with a meteorological station that recorded the daily weather. It featured a wind indicator and pressure and temperature sensors. In addition, a vertically pointed LiDAR was able to observe cirrus clouds forming in the region and snow falling in the polar atmosphere. These phenomena had not been observed before. The lander also had a robotic arm that could dig half a meter into the soil and deliver samples to the analyzer, a combination of 8 high-temperature ovens and a mass spectrometer. In one excavation, the cameras recorded a white substance which gradually disappeared. Given the temperatures and the time it lasted, it could only have been water ice that sublimated after it was exposed. The soil was slightly alkaline, and the presence of perchlorate, which kills bacteria, was not good news for those hoping for Martian life. Phoenix operated for 2 months longer than planned before the gathering winter completely shaded its solar panels. While the planet still had subterranean deposits of ice, there was precious little left at the surface, yet it was now understood that many of the red planet's features had been carved by running water. Samples analyzed from across the planet affirmed that water and nothing else had made these changes to the Martian landscape. Mars had once been more like Earth, yet it had lost its surface water and most of its atmosphere, and the question of life persisted. Could it have emerged in a warmer, wetter past? And could it still be present below the surface? The next Mars mission would be NASA's most ambitious yet. Known as Curiosity, the car-sized rover would be powered by a nuclear battery, making it immune to the dust problems experienced by Spirit and Opportunity.
7, 6.
Curiosity was launched on an Atlas V from Cape Canaveral in November 2011.
1. Main engine start, 0, and liftoff.
In mid-2012, it entered the Martian atmosphere heading for Gale Crater. The Jet Propulsion Laboratory monitored the entry closely, but had no control over events. In Mars's thin atmosphere, the parachute could only slow the heavy craft to around 320 kilometers per hour. Nearing the surface, the rover descent stage dropped out of the aeroshell and rockets kicked in. At this stage, radar was guiding the lander to the surface, and a small camera was recording images of the terrain below the rover. Next, Curiosity was lowered on a tether beneath the descent stage. This sky crane technique was used to avoid too much swirling dust exposing the rover to unnecessary danger. Everything had worked exactly as it was supposed to, and the American engineers were relieved. The landing had been the most precise ever. Before Curiosity could start work, its computer went through a checklist to make certain that all systems were operating correctly. It was a day before the rover deployed its camera mast and communications antennas. It's thought that Gale Crater is 3.5 billion years old, and that its sediments have been laid down first by water and then by wind. NASA now has a sophisticated mobile science laboratory on Mars, connected to Earth by the most advanced communications link, courtesy of the Mars Reconnaissance Orbiter. The rover's primary objective is to discover if conditions suitable for life ever existed or still exist on Mars. It's also gathering detailed information about the current conditions on the red planet, particularly the radiation levels that will have an impact on proposed manned missions. Curiosity has analyzed the dust from a number of holes it drilled, revealing sulfur, nitrogen, hydrogen, oxygen, phosphorus, and carbon, all elements essential to life. In its 6 years on the surface of Mars, Curiosity has traveled around 20 kilometers, but the driving is taking its toll. It routinely sends back a series of self-portraits, mainly for diagnostic reasons. Its wheels have taken severe damage, which will undoubtedly lead to design changes for future rovers. Its computers are also giving problems, but a new suite of missions is slated to arrive at Mars in 2020 that will continue profiling the planet. There is one aspect of the Martian environment that has never been investigated, but that's about to be addressed. The Mars InSight probe has been targeted at the flat Elysium Planitia, close to the equator, to spend 2 years investigating the planet's interior. It made a flawless landing in November 2018. After unfurling its solar array, it spent weeks selecting a suitable spot to deploy a seismometer onto the surface to monitor Marsquakes. It's clear that Mars had a warm, wet past, but it's cold and very dry now. Learning about the planet's geological activity will help us know why Mars has changed. The InSight probe also hammered a thermal sensor into the surface to gather data on heat flow from the planet's core. By understanding processes within Mars, we can learn how the geological histories of Mars and Earth began to diverge. The Earth is our home. Our natural environment results from complex relations between the sun, the oceans, and the atmosphere. The polar ice and the tropical heat represent the extremes of our planet's climate. In reality, this is a very narrow temperature band, completely different from any other planet we've observed. The stability of the Earth's environment has allowed life to emerge, and life has changed the planet. As far as we know, the Earth is the only planet in the universe to have given rise to life. The Orion Nebula is a vast cloud of gas and dust in the Orion constellation. It's a place where new stars are being created. As part of the nebula condenses, it separates into clumps. As each clump contracts under its own gravitation, it begins to swirl, flattening into a disk. They're called protoplanetary disks, or proplyds. In the center of a proplyd, as the molecules are squeezed together, a fusion reaction begins and a star ignites. Some proplyds, occurring close to an established star, shine brightly under the influence of their neighbor. While this makes them easier to observe, the glowing gas and dust is being stripped away by the stellar winds from the adjacent star. Dark proplyds, only observable as silhouettes, maintain their surrounding ring of gas and dust. As the system matures, this stellar debris will form a planetary system. The Hubble Space Telescope has recorded numerous examples of this process, enough for astronomers to understand that the formation of planets is commonplace. This is how our own sun started its life 4.6 billion years ago. But the planets would take longer to emerge. Small grains within the disk began accreting, forming planetesimals. The larger a clump became, the stronger its gravitational attraction, in turn leading to more rapid growth. An early version of Jupiter would have been the first to coalesce, completely clearing its orbit. Around a core of heavy metal and rock, Jupiter's atmosphere, mainly of hydrogen, was compressed by its strong gravitation. Any solid surface lay beneath thousands of kilometers of liquid gas. Our observations of exoplanets have revealed Jupiter-sized gas giants orbiting close to their stars. astronomers believed the young Jupiter would have begun a track toward the Sun, dragging asteroids and comets in with it. But Jupiter's inward path reversed as it was pushed into an orbital resonance with the emerging Saturn. Not all of the objects forming in the early solar system stayed orbiting the Sun. Smaller objects passing a planet would be deflected by the stronger gravitation, or even captured, becoming a moon. It is thought that there were up to 20 smaller planets orbiting in the inner solar system, from which the 4 remaining terrestrial planets were formed. At this time, collisions in the developing planetary system were common, and evidence from the Apollo moon rocks suggest an impact between the early Earth and an ancestor of our moon was important in our planet's evolution. The Earth has a larger than expected iron core, and gravitational analysis of the moon suggests its core is lighter than expected. A collision between the bodies would explain the moon's loss of much of its heavy material to the more massive Earth. The impact was a glancing blow that set the Earth rapidly spinning with a 5-hour day. The moon that we know coalesced from the molten debris. Although our moon is not the largest in the solar system, it is closer in mass to its parent planet than any other moon. The stabilizing effect that the moon has upon the Earth's rotation is significant. Over long periods, the Earth's axis will vary by as much as 1 degree. Without the moon's influence, this variation could be as much as 85 degrees, with drastic implications for the climate's stability. The debris in the early solar system was cleared by the planets in a period called the Heavy Bombardment. The emerging Earth was peppered with asteroids and comets, delivering water necessary for life. While tectonic forces erased the bombardment scars from Earth, the Moon, which endured the same travails, is still covered with craters. When chaos in the developing solar system settled down, the young Earth was in a unique position. The Earth's distance from the Sun was just right for the abundance of water on the planet to exist in liquid form. As the Moon had drifted away, the planet's rapid rotation had slowed, and the Sun's heat was evenly shared across the surface. The Earth's large metallic core, combined with the planet's rotation, meant that a magnetic field stretched out around the planet, deflecting the charged solar wind and protecting the surface from extremes of solar radiation. In a hostile universe, the Earth was a uniquely benign environment. The geological record shows that around 2.7 billion years ago, oxygen began occurring in the atmosphere. The vast iron ore regions of Western Australia were formed as iron in the oceans reacted with the new abundance of oxygen to form iron oxide. Simple plant life was using the sunlight and carbon dioxide to live, and it produced highly reactive oxygen as a waste product. This enabled more complex life to emerge, building an intricate web of interrelated plants and animals, completely transforming the planet. The change in the atmosphere had other dramatic consequences. Oxygen stripped much of the highly insulating gases from the air, drastically cooling the Earth. A sequence of ice ages began. Though there is an abundance of evidence showing planetary glaciation, punctuated by warm periods, the factors triggering these cycles are complex. Fault lines are clues to the movement of continents, leading to diversions of ocean currents. The effect of volcanic activity on the atmosphere. And changes in the direction of the Earth's axis with regard to our planet's elliptical orbit around the Sun, all contributors to long-term fluctuations in the Earth's climate. Analysis of ice cores deposited in the Antarctic or Greenland is an accurate way to see how the composition of the atmosphere has changed over the previous 800,000 years. Bubbles of air caught between snowflakes before being rigidly trapped as the snow becomes ice can be accurately sampled. One thing is clear. Carbon dioxide reaches a peak of around 270 parts per million during the warm periods and drops to approximately 170 parts per million when glaciation is at its greatest. But from this data, it's hard to know if extra CO2 causes the warming or the warming leads to extra CO2. In 1958, Dave Keeling, working for the Scripps Institute, began recording accurate levels of atmospheric CO2 at the Mauna Loa Observatory in Hawaii. It was the beginning of a unique record known as the Keeling curves. Keeling's graph revealed a seasonal variation corresponding to spring and summer in the northern hemisphere, where landmass and plant cover is greater. During the northern spring and into the summer, CO2 levels dropped because of the increase in photosynthesis. By the 1970s, a disturbing trend had emerged. CO2 levels were in a steady rise. At first, there was uncertainty about the implications. Extra CO2 could trap more heat, leading to a warming effect, known as the greenhouse effect. But some scientists were worried that aerosol pollution could attenuate levels of sunlight reaching the planet, resulting in a cooling environment. As the decades passed, different pieces of evidence were collected. Drill cores from the ocean floor revealed that ice ages had been triggered by Milankovitch cycles, the variations between Earth's tilt and its elliptical orbit. Though these effects were minor, the correlation was obvious. If such a small nudge could alter the climate, perhaps changes in CO2 could as well. Scientists were realizing just how poorly they understood planet Earth.
A Thor Delta rocket blasts aloft from Cape Canaveral, carrying a robot weatherman into orbit for America's...
At the beginning of the space age, scientists were keen to make weather observations from orbit. Launched in 1960, Tyros-1 was the first weather satellite. It was equipped with 2 TV cameras, regularly transmitting images of global cloud patterns. It provided meteorologists with a unique view, and it was followed by improved versions. Because these early satellites were in highly inclined low Earth orbits, the data gathered covered the whole planet, and it was shared across the world. Since 1873, nations had been cooperating on weather prediction via the International Meteorological Organization, which in 1951 became the World Meteorological Organization, an arm of the United Nations headquartered in Geneva. With a UN resolution calling for international cooperation in the peaceful uses of outer space, weather satellites of different nations were soon being coordinated for the benefit of all mankind. In 1964, the Nimbus program began. The series of 7 satellites included a more sophisticated set of sensors. Nimbus was a testbed for new technologies, and it gathered data about different areas. Along with cloud patterns was information about the atmosphere and sea ice. This was the pre-digital age, and all electronic image data was burnt to and stored on 70mm film. Little thought was given to establishing an archive for future reference. The Nimbus program was an early example of Earth observation rather than just a group of weather satellites. And meteorologists started seeing the planet as a complex and interconnected system. Today, a fleet of satellites is in operation, monitoring the atmosphere, the oceans, the ice, the land, and the biosphere. It is now understood that ice, particularly sea ice, plays an important role in the Earth's climate system. Polar ice slowly flows to the coasts where it melts, providing a source of cold water that drives the ocean currents responsible for the transfer of heat from the equatorial regions to the poles. These currents also move nutrition, which is important for the survival of life. Global winds also circulate water via clouds, keeping the land moist and able to support vegetation. Plant life in both the oceans and the atmosphere removes CO2 from the air and replenishes the atmospheric oxygen. Both the ice, known as the cryosphere, and the clouds reflect a proportion of the sun's energy back out into space. The extent of the ice and cloud cover are important factors in the Earth's energy budget. As ice melts, it exposes ocean or rock, which absorbs more solar energy. Similarly, cloud cover, or the absence of it, will have an effect upon the land or sea beneath. Vegetation is also an important climate factor, as land plants pump huge amounts of water vapor into the atmosphere. But things are changing. Humanity, simply through weight of numbers, is influencing key elements of the planet's climate system. In 50 years, the Earth's human population has risen from just over 3.5 billion to 7.7 billion today. More people need more resources. And while there have been revolutions in agriculture and in technology, the Earth's reserves are not limitless. In 1979, Europe began launching spacecraft. And while the new Earth observation satellites were revealing changes, scientists were reluctant to reach conclusions about long-term trends. They understood that there was a certain amount of variability in the planet's climate cycle. And though climate science knew about the steady rise in atmospheric CO2 revealed by the Keeling curve, researchers were looking for additional, solid evidence that change caused by human activity was happening. Since 1913, spectroscopy had revealed that a layer of ozone in the stratosphere blocked harmful UV sunlight from reaching the ground. In 1974, Mario Molina, a postdoctoral fellow working on hot atom chemistry, published a paper suggesting that the family of industrial chemicals known as chlorofluorocarbons, or CFCs, could damage the ozone layer. In the 1980s, meteorologists working in Antarctica found the evidence. The polar vortex above the southern continent concentrates the CFCs in the stratosphere. Mother-of-pearl clouds in the polar skies contain ice crystals which, in combination with ultraviolet, split chlorine from the CFC molecule. Each chlorine atom can break down over 100,000 ozone molecules. A large area centered over Antarctica showed almost no ozone. It became known as the hole in the ozone layer. The United Nations began talks aimed at limiting the production of CFCs, and in 1989, an international treaty, known as the Montreal Protocol, capped the production of CFCs and ultimately resulted in a 10-year phase-out of CFC production. All countries signed the agreement, and the Montreal Protocol is seen as a model of international cooperation. In the 1980s, an upward trend in global temperature averages was becoming clear, and a scientific consensus emerged that the burning of fossil fuels was altering the balance of gases in the atmosphere. Most of our planet's fresh water is locked in the polar ice caps. 61% of this ice covers the Antarctic continent. In the north, Greenland is also covered by an ice sheet. There is no landmass at the North Pole, but a large area of sea ice grows and shrinks with the seasons. Seasonal sea ice also fringes Greenland and Antarctica. Ice shelves are a third manifestation of polar ice. These are thick layers of ice that extend into the ocean from the mouths of glaciers. Periodically, icebergs will break away from these regions. These areas are important to the circulation of global winds and ocean currents. And since 2002, NASA has tracked the prevalence of water in general and ice in particular via the GRACE satellites, which were recently replaced by a similar pair of GRACE follow-on satellites. The two follow the same orbit, and minute changes in the Earth's gravitational field will cause them to change speed with a variation in the distance between them. This data is accurately measured, allowing researchers to record changes due to variations in groundwater or in ice thickness. During the life of the first GRACE mission, Greenland lost 285 gigatons of ice per year. On average, Antarctica lost 137 gigatons per year. From 2005 to 2016, sea levels rose by 3.7 centimeters due to melting ice sheets and to expansion of seawater. Sea levels have been monitored from space since 1992, initially with the TOPEX Poseidon satellite and more recently with the JASON series of satellites. JASON 3 uses a precision radar altimeter to measure regional and global variation in sea levels. In the 20 years to 2014, the average rise was 6 centimeters, but the increase is not uniform. The red areas show the greatest rise, with white representing no change, and blue signifying a decrease. The unevenness of the sea surface is due to a complex interaction between ocean currents, the Earth's spin, and the topography of the ocean floor. All these factors must be accounted for to arrive at a baseline against which to measure changes. These blue areas in the Atlantic show a shift in the Gulf Stream. The Camargue region of southern France is a low-lying area at the delta of the Rhône River. In the 1980s, a seawall was built to prevent the encroaching Mediterranean. Over the last 30 years, the coastline here has been pushed back by several hundred meters. Scientists are convinced that a warming global climate is responsible, and that our reliance on the burning of fossil fuels has led to an excess of carbon dioxide in the atmosphere, which traps heat. 93% of this heat has been taken up by the oceans. Data from the Argo network of ocean buoys shows an average warming of 0.9 of a degree Celsius since the 1950s. While this may not sound like much, meteorologists understand how sea surface temperatures drive hurricanes and cyclones, and early predictions of storms of greater magnitude are being realized. Long-standing weather records are being broken and broken again. In 2017, NASA, NOAA, and the UK Met Office all agreed that 2016 had been the hottest year on record. Globally, 16 of the 17 hottest years have all occurred since the year 2000. Both NASA and ESA have been monitoring the distribution and concentrations of CO2 in the atmosphere since 1992. This visualization from data collected in 2006 shows the yearly fluctuations of carbon dioxide and carbon monoxide. While most CO2 emanates from the populous northern hemisphere, seasonal fires in Africa, Australia, and South America generate much of the carbon monoxide. Prolonged droughts and more severe forest fires are another aspect accompanying increased levels of atmospheric CO2 that are currently unfolding. Such events inject a huge pulse of greenhouse gases into the atmosphere, magnifying the problem. The European Space Agency's Copernicus program, with its Sentinel Earth observation satellites, has committed to making information about the changing climate freely available to policymakers, businesses, and research institutions. Josef Aschbacher is ESA's Director of Earth Observation Programs.
What you see here on this graph is the CO2 concentrations of the atmosphere over the last 800,000 years. And you see that these values are going up and down in different phases. You see on the blue lines here are indicating ice ages, and the orange lines here are indicating periods between ice ages or periods where it's much warmer. But you also see that over the last 800,000 years, the value was always below 300 parts per million, and suddenly, since the last century, it goes up very steep towards 400 parts per million or even beyond.
Distinguished delegates,
the recent climate summit, COP25, held in Madrid, made little progress toward an international agreement to cut greenhouse gas emissions. While some businesses and economies will have to adjust, that task only gets more difficult as time passes, and far greater adjustments will be forced upon everyone. The Earth is the only place we know that harbors life, but the stability that has enabled this web of life is fragile. Plants and animals interact for mutual benefit. Our benign environment results from the complex and varied creatures with which we share the planet. It's important that we look after our home. Some of our solar system's planets have been visited by scientific probes less frequently than others. The outer gas giants, Uranus and Neptune, are so distant they're hard to reach. Uranus is 20 times further from the Sun than Earth, while Neptune is 30 times further. Both have only been seen at close range by NASA's Voyager 2 spacecraft. Mercury is so close to the Sun that any probe sent in its direction must take a circuitous path to offset the Sun's immense gravitational influence. The Mariner 10 probe flew past Mercury in 1973, and the Messenger probe went into orbit around Mercury in 2011. Venus presents different problems. Though it's our closest planetary neighbor and easier for spacecraft to reach, dense cloud hides its features and its surface has hellish conditions. The Russian Venera craft have landed, but in the hostile environment, they could only survive for minutes. Roughly twice every century, the planet Venus passes between the Earth and the Sun. Called the Transit of Venus, it was closely observed in 1769. Astronomers realized that careful timing of Venus's passage across the face of the Sun would allow them to calculate the distance to the Sun, which in turn would unlock far more accurate methods of navigation. In 1961, the Soviet Union launched Venera 1, the first Venus probe. It passed Venus as intended, but Mission Control had lost contact with it. The following year, NASA launched Mariner 1 to Venus.
We're not on trajectory.
A coding error led to control problems with the launcher.
Destruct command.
It was destroyed minutes after liftoff.
Blew up.
Because convenient launch opportunities only occur in 18-month cycles, NASA had a second probe ready to launch. Mariner 2 was essentially a Ranger spacecraft designed to go to the Moon. These were the early days of the space race, and the United States was desperate to catch up with the Soviet Union. Lead times were short, and the Jet Propulsion Laboratory did not have time to complete its original design. In August 1962, Mariner 2 was launched. The Ranger spacecraft launched toward the Moon had all failed. Mariner 2, on its way to Venus, was functioning, but its transmissions were weak, and due to a launch anomaly, it was off course. After a week, instructions for a complex course correction were transmitted to the spacecraft. About an hour later, Mariner executed the maneuver, which involved a roll turn, followed by a pitch turn, and finally a main engine burn. It worked well, but several days later the craft lost lock on the Sun and the Earth, its two attitude reference points. It corrected itself before ground control could diagnose the problem. Next, the signal strength increased to its normal level, but a short in a solar panel left it low on power. At this time, although both America and the Soviet Union had been sending probes toward the planets, nothing had succeeded. Mariner 2 lost several telemetry sensors and it began to overheat. It continued limping toward Venus, but some of the spacecraft's problems were solving themselves. Mariner 2 was now close enough to the Sun that it could function effectively on just one solar panel. It passed slightly less than 35,000 kilometers above Venus's cloud tops. It could detect no planetary magnetic field, and it recorded temperatures across the planet approaching 500 degrees Kelvin. Clearly, landing on the surface would present problems. But America wanted to focus on their first real success in space, finally doing something that the Soviets had not. Mariner 2 was the first successful interplanetary probe, and in California, the home of JPL, they celebrated. The next major advances in the exploration of Venus were made by the Soviet Union. The objective of the Venera series was to land on the surface of Venus. Designers understood that not only were the surface temperatures hot enough to melt lead, but that the atmospheric pressure was many times that of Earth. The landers they built looked more like diving bells than spacecraft. In June 1967, Venera 4 was launched. The vehicle consisted of a carrier craft with instruments used during the cruise phase to Venus and a spherical landing module that could communicate independently. After entry into the atmosphere, Venera 4's parachute opened. It sent back data for 93 minutes, but stopped 28 kilometers above the surface. Yet its electronics hadn't been overwhelmed by the heat. It had simply run out of power. Extrapolations from its final measurements showed a surface temperature of 500 degrees Celsius and a pressure of 75 atmospheres, far higher than anyone expected. The Venera program strengthened its landers and fitted smaller parachutes to reduce descent time. Launched in January 1969, Venera 5 and 6 learned more about the chemical makeup of the atmosphere, but neither remained functioning at the surface. The Venera series continued, refining the technology and making incremental improvements to mission duration, adding to the knowledge about Venus. In 1975, Venera 9 was launched. It was a new design, consisting of an orbiter-lander combination, with the orbiter able to act as a relay station for signals transmitted from the surface. 4 months after launch, the orbiter and the lander, encased in a spherical shell, separated. It entered the atmosphere 2 days later, while the mother craft became the first probe to go into orbit around Venus, photographing parts of the surface in ultraviolet. The new lander had a ring shield that could replace a parachute during the latter stages of the descent through the dense atmosphere. Venera 9 transmitted the first black and white pictures from the surface, though a design fault meant a second camera could not eject its lens cap. 3 days later, and 2,000 kilometers away, a twin craft, Venera 10, landed. It took pictures too, but the same design fault left a lens cap stuck in place. Both landers had been pre-cooled while still in space, and circulating cooling fluid kept the craft operating on the blistering surface for more than an hour. In 1983, 2 more Venera craft arrived at Venus. Equipped with synthetic aperture radar, they made the first serious attempt to map the surface beneath the cloud layer. Over 8 months, they mapped from the North Pole down to 30 degrees north.
T-minus 10, 9, 8, 7, 6.
NASA had taken a minor role in the early exploration of Venus. But in 1989, the space shuttle Atlantis lifted off carrying the Magellan probe. Magellan was bound for Venus. Like the Venera craft before it, Magellan would use radar to map the surface of the planet. It was the first interplanetary spacecraft launched from the space shuttle. Following a cruise of 15 months, Magellan arrived at Venus and entered an elliptical orbit. To keep costs down, the probe had been built from an agglomeration of spare parts left over from previous NASA missions. After some software problems, it began mapping. The images it relayed remained the highest resolution pictures we have of the surface of Venus. Pictures of low volcanic blisters emerged, and lava channels were evidence of an extremely active surface. The thick atmosphere has prevented all but the largest meteors reaching Venusian ground, and few impact craters were visible. Yet evidence of plate tectonics that sculpts the Earth's surface was not obvious. After mapping Venus, Magellan changed its orbit and plotted the planet's gravitational anomalies. On Venus, localized changes in gravity correspond to surface features. On Earth, this is not the case. A new naked picture of Venus emerged. The surface appears to have been completely remade around 500 million years ago. Yet while volcanoes and lava channels are common features on Venus, Magellan could not find evidence that volcanic activity still happens on the planet. In 2006, the European Space Agency's Venus Express went into orbit around Venus. Its focus was the long-term analysis of the planet's atmosphere. During its 8-year mission, it registered a sharp rise in the atmosphere's sulfur dioxide. This could be due to changes in wind patterns, but it could also be a sign of volcanic activity. Researchers also saw increases in infrared radiation coming from 3 different volcanic locations. More circumstantial evidence of current volcanic activity. Finally, the infrared team saw short-term temperature changes that fluctuated over just a few days. It appears that volcanoes may still be active on Venus. The mission ended in 2015 with a series of swoops into the upper atmosphere that verified unexpected ripples in the mesosphere. Very little in the way of Venus exploration has happened since Venus Express. Though elaborate plans exist for future missions to Venus, nothing at this stage has been funded. Yet many missions still pass close to Venus to use its gravitation to alter their flight paths. In 1974, Mariner 10 was the first spacecraft ever to use the gravitational slingshot effect on its way to Mercury. Italian mathematician Giuseppe Colombo devised the maneuver as a way to save fuel and to fly past Mercury not once but several times. The technique is now commonplace. 10 days after launch, Mariner 10 executed instructions for a routine course correction. This appeared to go well, but after the burn, when the craft attempted to reorient itself, there was a problem. Mariner 10 knew where it was pointing because its tracking sensor could lock onto the star Canopus, but a flake of paint that had come from the spacecraft was confusing the system. An automated backup procedure found Canopus again, but flaking paint was an issue for the rest of the mission. To reach Mercury, a spacecraft must approach the Sun, and its immense gravity presents a problem. Voyages to outer planets are constantly slowed by solar gravity, but with the inner planets, a spacecraft constantly accelerates. Mariner 10 used Venus's gravity to reduce its speed, and it approached Mercury at an acute angle. Mariner 10 did not have enough fuel to go into orbit around Mercury, but its sun-centered path allowed the probe to make 3 close passes. Its first pass revealed a moon-like planet with a heavily cratered surface. Though Mercury is the smallest planet, it's the most dense. It has a large, iron-rich core. Prominent escarpments were seen. Here, Discovery Scarp cuts through 2 craters. It falls 3 kilometers. It's thought that these cliffs are the result of cooling and shrinking of the core. Mariner 10 continued to suffer technical problems. Its tape recorder kept sticking. There were restrictions in the rates of data transmission, and limited attitude control meant flight engineers were using solar pressure on the high-gain antenna and solar panels to compensate. Yet the mission continued. Mariner 10 could only map about 45% of Mercury's surface, as the same hemisphere faced the Sun during each of its passes. Mariner 10 discovered a very thin atmosphere, primarily of helium. Several months after its third and final pass of Mercury, it ran out of fuel. It still orbits the Sun.
Main engine start, 2, 1, and 0.
It was more than 30 years before the next mission to Mercury. In 2004, Messenger was launched. It was designed to go into orbit around Mercury, which presented a number of design constraints. It featured a large woven ceramic sun shield, but it did not have a dish antenna. It would rely on a phased array that could be electronically pointed. After a year in space, Messenger was back at Earth, using its gravitation to modify its orbit. Even though it was not a large spacecraft, it had a powerful engine for course corrections and orbit insertion. It continued on to pass Venus twice to lose speed as it drew closer to the Sun. 3.5 years after launch, Messenger approached Mercury, but this was not the end of its journey. The probe made 2 more passes of Mercury before finally going into orbit after almost 7 years in space. Mission engineers had the extra problem of always requiring the probe's sun shield to be pointed toward the Sun. Because it was in orbit, Messenger was able to complete the mapping started by Mariner 10. The planet's dominant feature is the Caloris Basin. It's an ancient crater more than 1,500 kilometers across. Mariner 10 saw some of the area, but the rest had been in darkness. This map of the southern polar region uses color to represent illumination. Because Mercury's axis is not tilted, sunlight cannot penetrate deep craters near the poles. It was in these areas that Messenger discovered substantial amounts of water ice. Messenger received several mission extensions, but in 2015 it crashed into Mercury after running out of fuel. A new mission is already on its way to Mercury, Bepi Colombo, named after the designer of Mariner 10's trajectory. It's a joint effort between JAXA, the Japanese Space Agency, and the European Space Agency. It will take 7 years to reach Mercury. The Voyager 2 spacecraft is the only probe to have made close approaches to the two outer ice giants, Uranus and Neptune. Launched in 1977 with its twin Voyager 1, it was able to take advantage of a rare alignment of the four outer planets, enabling it to make close observations of each one. In 1986, Voyager approached Uranus. In the distant past, it must have been hit by another massive body that knocked its axis sideways. Uranus has an east and a west pole, and for half its orbit, one side sees continual sun, while the other remains in darkness. It has rings which follow its north-south equator. Voyager 2 discovered 11 new moons and a misaligned magnetic field. Images that the Voyager captured showed Uranus as a bland, featureless planet. But this was because of its particular season. With images from the Hubble Space Telescope, we now know that at certain times clouds and planetary weather appear in the atmosphere. Uranus's largest moon, Miranda, was observed in detail for the first time. So chaotic is its surface that researchers thought that it must have been blown apart by some cosmic impact, with the fragments reforming. Now it's thought that tectonic forces, initiated by the gravitation of Uranus, are responsible for the moon's jumbled appearance. As Voyager 2 left Uranus, backlighting from the sun revealed two new rings encircling the planet. The spacecraft was now heading toward Neptune, the solar system's last planet. In the 3 years it would take to get there, ground engineers began preparing for unique challenges. Neptune is 30 times further from the Sun than the Earth, and the light intensity is 1,000th what it is here. For photography, time exposures would be necessary, yet Voyager 2 was traveling so fast that images would smear without special preparation. Engineers calculated just how much the craft would have to swivel while exposures were made to compensate for the probe's movement. In June 1989, Voyager 2 began returning distant images of Neptune. Across the world, people had realized that the data sent back to Earth by this spacecraft was transforming our understanding of the solar system. This was before the internet age. Researchers at the Jet Propulsion Laboratory clustered around TV sets to watch as data and images came in line by line. Neptune is a more conventional planet than Uranus. Its axial tilt is 30 degrees, and it revolves in the same direction as Earth. While Neptune is slightly heavier than its fellow ice giant Uranus, it has a slightly smaller diameter. And, though it is further from the Sun than its neighbor, Neptune emits more heat than Uranus. The planet has an internal heat source that drives more dynamic weather patterns. Voyager 2 measured wind speeds at Neptune in excess of 2,000 kilometers per hour, the fastest in the solar system. There were cirrus clouds in the atmosphere, and the probe recorded pictures of a great dark spot, similar to Jupiter's Great Red Spot. It was an anticyclone in the southern hemisphere as large as the Earth. In 1994, when Hubble tried to find the same feature, it had disappeared, but a new dark spot was forming in the northern hemisphere. Voyager 2's last observations within the solar system were of Neptune's largest moon, Triton. Unlike all other moons in the solar system, Triton has a retrograde orbit, indicating that it was not formed at the same time as the planet, but that it had been captured. As Voyager 2 moved beyond the planets, its cameras were switched off to save power. Both Voyagers continue away from the solar system, measuring the influence of the solar wind. This remains the only mission to the ice giants. On January the 19th, 2006, an Atlas V was launched. It was a very powerful rocket with an unusually small payload. New Horizons left Earth orbit faster than any other probe. It was headed for the Kuiper belt at the outer edge of the solar system, in particular Pluto. In a little more than a year, New Horizons reached Jupiter, where it received a gravitational assist that cut 3 years from its flight time to Pluto. After it passed Jupiter, the spacecraft went into hibernation, simply sending an all's well transmission once a week. It took New Horizons more than 9 years to reach Pluto. Since it had departed, Pluto had lost its status as a planet. With the discovery of more objects of similar size in the Kuiper belt, it was decided that to be a planet, a body had to clear its orbit. Pluto's features surprised everyone. Here was a living planet shaped by tectonic forces, but instead of rock, the mountains were made of ice and frozen methane. And Pluto has a thin atmosphere, mainly of nitrogen. The probe continued on over Charon, Pluto's largest moon. Its icy surface has deep canyons, and some evidence suggests that it has ice volcanoes. Charon is about half the size of Pluto, and the two orbit each other. From Pluto, Charon would appear motionless in the sky. As the New Horizons probe sped away from Pluto into deep space, it began the slow process of transmitting its recorded data back to the Earth. At these distances, it takes signals 4.5 hours to reach Earth, with data coming in at 1 kilobit per second. It took 469 days for all the Pluto information to be received back on Earth. Early in 2019, New Horizons passed trans-Neptunian object Ultima Thule, and with a mission extension, it continues exploring the outer reaches of the solar system. Our Sun is a star like billions of others throughout the universe. It's a giant nuclear furnace at the center of our planetary system. And although life on Earth is completely reliant upon the Sun, we also need our planet's magnetic field and atmosphere to protect us from extremes of solar radiation. Regularly, the Sun ejects huge blasts of solar plasma, and on Earth, a direct hit by a coronal mass ejection will play havoc with power grids, communications, and satellites. 1859 was a year of extreme solar activity. During September of that year, astronomer Richard Carrington was sketching sunspots when he observed an intensely bright event. Less than 18 hours later, auroras were seen around the world. They extended to low latitudes where the phenomenon is rarely seen. Telegraph operators across Europe and North America reported malfunctions, including electric shocks and sparking wires. This was the first time that solar storms had been linked with auroras and electrical and magnetic disturbances here on Earth, and it became known as the Carrington effect. Since the 1700s, a periodic fluctuation had been observed in the number of sunspots, but a deeper insight into the sun's behavior would not emerge until 1958. James Van Allen was the chief scientist for America's first satellite, Explorer 1. It was equipped with a cosmic ray detector.
8, 7, 6, 5, 4, 3, 2, 1. Fine, commanding, command.
The launch was successful, but the orbit achieved was highly elliptical with an apogee far greater than expected. As its altitude changed, variation in the detector's readings suggested that charged particles were trapped in bands around the Earth. These became known as the Van Allen belts. It was a discovery with far-reaching implications. The energetic charged particles that make up the Van Allen belts emanate from the Sun and are trapped by the Earth's magnetic field. They fluctuate with solar activity, and they present a risk to spacecraft that have to pass through them. The previous year, physicist Eugene Parker, working at the University of Chicago, had predicted that a constant stream of charged particles would flow from the Sun. He called it the solar wind. The astronomical community was reluctant to accept this idea. Soon, his theory was vindicated, as early Russian and American spacecraft began detecting a constant stream of charged particles. Solar wind explained why a comet's tail always points away from the Sun. Parker's supersonic solar wind theory predicted a variable stream of plasma, charged particles, permeating the solar system. The Earth's magnetic field deflects most of the solar wind, preserving the Earth's atmosphere. In 1995, the Solar and Heliospheric Observatory was launched. SOHO monitors the Sun from a point where the gravity from Earth and from the Sun exert equal force, keeping the probe in a stable orbit. SOHO gives us a clear picture of the solar wind. Its LASCO instrument obscures the central disk of the Sun, revealing the corona, the Sun's atmosphere. The planets are also clearly visible. The horizontal lines flanking them are due to their brightness overwhelming the camera's sensor. SOHO's extreme ultraviolet imaging telescope was able to see waves traveling out from solar flares, causing snow-like interference in the image sensor. Solar radiation in the extreme ultraviolet varies from minute to minute and over the Sun's 11-year solar cycle. Solar activity generates tides in the Earth's atmosphere, which increase with altitude. This, in turn, adds to the drag felt by low-orbiting satellites. Communication systems can also be affected, in particular GPS services. Constantly monitoring the Sun's behavior is important, and in 2010, NASA launched the Solar Dynamics Observatory. It orbits the Earth geosynchronously at an inclination of 28 degrees, which gives it a constant view of the Sun. The SDO observes in a number of different wavelengths that correspond to different temperatures, each one revealing varying activities, from the surface to the corona and to the flaring regions. The Sun is not solid. Rather than rotating, it swirls. At the equator, it spins once every 25 days. At the poles, it takes 38 days. It's in a plasma state, extremely hot matter made up of loose electrons and ions. Plasmas are excellent conductors of electricity, and the movement of the sun generates a tangle of magnetic field lines. The surface of the sun, known as the photosphere, has a temperature of around 6,000 degrees Kelvin and is best viewed in the visible part of the spectrum. Here, sunspots appear as dark regions where magnetic flux impedes convection. These are about the size of the Earth. Beyond the visible spectrum, magnetic loops at the same areas become visible. The lower levels of the Sun's atmosphere, the chromosphere, see gravity yielding to the dynamic thermal and magnetic forces, with temperatures increasing to 8,000 degrees Kelvin. Ascending further through the solar atmosphere, a narrow band called the transition region sees temperatures rise to more than 500,000 degrees Kelvin. In the corona, seen here during an eclipse, it rises to 1,000,000 degrees Kelvin. Why this happens is not understood. The atmosphere is where the solar weather is generated. Solar flares appear as bright flashes, bursts of electromagnetic radiation from radio waves to gamma rays. Solar flares from some other stars are much larger than those from our Sun, and sometimes smaller stars, known as red dwarfs, display extreme solar flares. The Swift Gamma Ray Observatory is designed for rapidly locating brief bursts of gamma rays and X-rays. In April 2014, Swift saw a solar flare emanating from DGCVN. Its initial blast was 10,000 times stronger than any flare from the Sun. It was the first of 7 flares that continued for 2 weeks. DGCVN is a red dwarf, about 1/3 the size of the Sun, and it rotates twice as fast as the Sun. This enables it to generate a much stronger magnetic field. It's thought that the strength of the star's magnetic field is related to the intensity of the flares it emits. Coronal mass ejections are different. They are vast clouds of plasma blasted from the Sun's outer layers. They travel with the solar wind. While they are often linked with solar flares, researchers have not been able to establish a direct relationship. Observing the Sun in different wavelengths yields very accurate temperature readings, and the dramatic rise in temperatures moving away from the surface had scientists completely baffled.
Five, four, three.
In 1990, a new spacecraft was launched.
Ignition and liftoff of Discovery and the Ulysses spacecraft bound for the polar regions of the Sun.
The Ulysses probe was bound for the Sun, but had to go the long way. Solar researchers wanted to have a different view of our star. The solar system coalesced from a vast cloud of gas and dust. As it collapsed, it began to spin, forming a disk. All the planets orbit along the plane of this disk, called the ecliptic. Ulysses would look at the poles, the parts of the Sun that could not be seen from our terrestrial viewpoint. Ulysses traveled via Jupiter, using the giant planet's strong gravitation to change its course. It approached on a path that took it over the planet's north pole. This bent the probe's trajectory beneath the ecliptic so that it could see the Sun from a polar orbit. From Ulysses, we learned that the Sun's magnetic field reverses every 11 years, and that the solar wind from the more dynamic South Pole was faster than from equatorial regions, yet the South Pole had no clear location. The only thing clear about the Sun was that it keeps changing.
5,
Now, heliophysicists wanted to be able to see the face of the sun that was not seen from Earth.
Liftoff of the Delta II rocket with stereo, giving us a three-dimensional look at the physics of our sun.
The twin stereo probes were launched in 2006. They were in slightly different orbits, one leading the Earth and moving slightly faster, the other trailing the Earth and moving slower. Each year, the two craft separated by 44 degrees, giving each an increasingly different view of the sun. Because the sun rotates, sunspots can develop out of sight. As sunspots are key indicators of solar weather, it's important to know just what is about to spin into view. The stereo probes now observe the sun in 360 degrees. This makes it much easier to plot the direction of coronal mass ejections. Though these happen with reasonable frequency, most will miss the Earth. If they hit, they create havoc in electrical systems and trigger substorms in the planet's magnetosphere. Information provided by the stereo satellites is being used for the protection of power grids and satellites through regular space weather bulletins. Since the 1960s, observers had been aware that auroras would sometimes brighten suddenly, with movement within the auroral curtains increasing. These were short-term phenomena, quite distinct from solar storms that result in auroral activity lasting days. As communication satellites in geosynchronous orbits became more sophisticated, they registered sudden localized falls in the Earth's magnetic field that seemed to coincide with what were now being called substorms.
3, 2, 1. We have ignition and liftoff of a Delta II rocket carrying Themis, NASA's revolutionary journey to study the northern lights.
The Themis constellation of satellites was designed to monitor the behavior of the Earth's magnetosphere. The aim was to measure fluctuations within the Earth's magnetic field and relate any variations to changes detected in the auroras from ground stations in the North American Arctic. Each satellite was equipped with an array of booms to measure the strength and direction of electrical and magnetic fields. After several months, they maneuvered into elliptical orbits of varying eccentricity, with each reaching a high point above the night side of the Earth. The Earth's magnetic field deflects most of the plasma from the Sun. At times of high solar activity, some of the charged particles will spiral into the poles on Earth's day side. On the night side, the field lines are stretched to breaking point, called magnetic reconnection, when the plasma suddenly rebounds along the field lines into the polar regions. In February 2008, two of the probes detected a reconnection event, and 96 seconds later, the ground stations registered a sudden brightening of the aurora. The giant loops bursting from the Sun's surface are known as flux ropes. They are one of the most basic configurations in plasma. The glowing plasma follows helical magnetic field lines twisting around a central core. The Themis satellites discovered that flux ropes can extend all the way from the Sun to the Earth's upper atmosphere, carrying currents as high as 650,000 amps. Heliophysicists remained baffled by the behavior of the Sun's atmosphere, so a new probe was constructed. Known as IRIS, it was small and simple. It consisted of a telescope, an imaging spectrograph, and ancillary support equipment. It was cheap to build and cheap to launch. IRIS was placed in a polar orbit of the Earth that gave it an uninterrupted view of the Sun. It was able to look at the edge of the chromosphere where the plasma began its steep increase in temperature. Its images were far more detailed than had been delivered by any other probe and it could discern rapid changes. The waving jets of plasma, called spicules, were revealed in great clarity. There are roughly 10 million spicules across the Sun's surface at any given moment. They can grow to 10,000 kilometers, yet they collapse in 5 or 10 minutes. Researchers have made computer models of the spicules that behave in the same way as the images from Iris. It is thought that they form through the interaction of charged and neutral particles with the tangled magnetic fields. It seems magnetism must play an important role in the heating of the solar corona and in the high-speed ejection of plasma, but the mechanism is still not understood. There are at least 20 different satellites currently monitoring the Sun's behavior. Most are in orbit around the Earth. While it is important to get beyond the Earth's atmosphere to analyze the solar wind, it has not been possible to get really close to the Sun. Heliophysicists know the particles of the solar wind change not long after they leave the corona. If these particles could be sampled close to the Sun, it would reveal what part of the solar atmosphere was responsible for their extreme heat and their ultra-high speed. Until recently, it was not possible to build a craft capable of withstanding the temperatures in regions that scientists wished to explore. The team behind the Messenger probe to Mercury solved some of these problems with a woven ceramic sun shield which had to face the Sun at all times. Around 2010, work began on Solar Probe Plus, designed to pass the Sun just 6 million kilometers above its surface. A number of different systems have to work in concert to enable the probe to gather data inside the Sun's atmosphere. A carbon composite solar shield surfaced with highly reflective alumina will shade the rest of the craft from temperature extremes. As the Sun is a wideband radio source, the probe is out of contact during its close approaches and must function autonomously. In 2017, the probe was renamed the Parker Solar Probe after Eugene Parker, the physicist who had first identified the solar wind. It was the first spacecraft to be named after a living person.
On a mission like this into new territory, you're going to be in for some surprises. Maybe not big ones, maybe only little ones, but you're going to find that your point of view will have to change to conform with the data. Why is the solar corona, the outer atmosphere of the Sun, at 1 million or 2 degrees when the Sun itself is only 5,600? It isn't because of sunshine, that's for sure. Again, we don't know until we make the flight and have a year or two to think about the data.
The Parker probe's launch weight is less than 700 kilograms, which is quite modest. Yet its launch vehicle, the Delta IV Heavy, is one of the most powerful boosters available.
Minus 15.
In the pre-dawn hours of August the 12th, 2018, the final countdown was proceeding. Eugene Parker was at Cape Canaveral to watch the launch.
3, 2, 1.
There we go.
The probe was headed for 26 highly elliptical solar orbits over 7 years. During its mission, it will make 7 close passes of Venus, slowing each time to sweep closer and closer to the Sun. After separation from its upper stage, the probe first deployed its solar panels. These fold back near the Sun, with a cooling system enabling them to survive. The magnetometer boom unfolded at the rear of the craft, and then the field antennae, to measure electric and magnetic fields and waves, snapped into place. Though the Parker probe leaves Earth at high speed, it uses Venus's gravity to slow down, allowing it to approach the Sun at the appropriate angle. However, as it falls toward the Sun, it will accelerate to 720,000 kilometers per hour. On its outward loops, it will lose speed, but as the mission progresses, the Parker probe will make closer passes at higher speeds. It made its first close approach of Venus after just 52 days. 1 month later, Parker approached the Sun. For 11 days, it was out of contact with mission control, quietly recording data while carefully keeping its sun shield pointed directly at the Sun. Though the heat in this region is extreme, the particle density is not. The sun shield will reach around 1,500 degrees Kelvin, and the protected electronics of the spacecraft will be at room temperature. As the probe loops away from the Sun, it's able to re-establish radio contact and play back the stored data. This is the first image from inside the Sun's corona, taken during Parker's first pass. It shows a coronal streamer. The bright spot is the planet Mercury. The dark spots are image correction artifacts. The Parker probe's second and third passes were at much the same distance and speed as the first, but subsequent passes will be both lower and faster as it continues to use Venus to modify its orbit. In 2024, the Parker Solar Probe will visit Venus for the last time, and its final 5 passes of the Sun will come down to 6.2 million kilometers from the surface. By this time, we should have a clearer understanding of the processes that heat the solar wind and expel it at such high speeds. But whatever we learn about our Sun, it will raise new questions. A clearer understanding of the Sun has led to design changes in satellites and revised management practices of power grids and communication systems. But with new proposals to send humans back to the Moon or on planetary expeditions, we will need to understand more about the potentially hostile solar weather that flows from the star we call our Sun. There are 100 billion stars in our galaxy, the Milky Way. Or maybe there are 200 billion, or maybe 400 billion. No one really knows. In the universe, there are 100 billion galaxies, and as technology improves, that number could increase to 200 billion galaxies. No one is certain. At the start of the 20th century, there was only one galaxy, our own. Clearly, over the past 100 years, our knowledge of the universe has expanded, but there's still a long way to go. After more than 40 years, Voyager 1 has left the influence of the solar wind and is heading for interstellar space. Most of its instruments have been switched off and its nuclear battery is running low. It will be many thousands of years before it reaches anything other than interstellar debris. By then, the craft will be long dead. Cosmic distances are so vast that sending a probe to investigate anything beyond our solar system is not practical. The only realistic way we have of exploring the universe beyond our neighborhood is by examining the light that reaches us. The telescope is the main tool we have for this investigation. And for centuries, astronomers have been building ever larger instruments to see deeper into the cosmos. In the 20th century, conventional telescope design reached its limit. Past 8 meters in diameter, the curved primary mirror becomes so heavy that it will sag. As it is aimed at different targets, its precise curve is distorted by the effects of gravity. In addition, any extra resolution gained by the larger mirror is not delivered because of atmospheric distortion. One way to solve both these problems is to put a telescope in space. The Hubble Space Telescope is the best-known example. While the absence of atmospheric distortion was a breakthrough producing very sharp images, both operational and maintenance costs are considerable, and there are launch constraints on the size of a telescope that can be delivered to orbit. But engineers have developed a new generation of Earth-based telescopes with segmented mirrors that overcome the limits to size and can nullify much of the distortion caused by the atmosphere. The twin Keck telescopes on Mauna Kea in Hawaii were early adopters of this technique. Both have 10-meter mirrors, each in 36 hexagonal segments. Sensors monitor the mirror's shape, and actuators behind each segment continually correct for any distortions to the curve. The system is called active optics. A similar system that works at a more rapid rate monitors the stability of a bright guide star, or an artificial guide star generated by a laser. The adaptive optics system reads wavefront changes in the atmosphere, then adjusts the mirror's shape to minimize any distortion. This image of Jupiter, using adaptive optics, rivals those captured by an orbiting telescope. Observatories are located at high altitude, where the air is dry and there is no light pollution from nearby cities. The European Southern Observatory has clusters of telescopes at several sites high in Chile's Atacama Desert. At Paranal, 4 identical large telescopes each have 8.2-meter mirrors. They can combine their light using interferometry. In addition, 4 auxiliary 1.8-meter telescopes can link into the cluster. Collectively, they are the Very Large Telescope Interferometer, or VLTI. Visible light is just a small part of the electromagnetic spectrum. ESO has another facility northeast of Paranal on the Chaknantor Plateau. Here, an array of 66 radio dishes observe in millimeter and sub-millimeter wavelengths. They are linked and also function as an interferometer. Observing in the microwave part of the spectrum is particularly useful, as these frequencies penetrate gas and dust clouds that remain opaque to higher energy signals. The more widely the telescopes are separated, the better the angular resolution they can deliver. This property led radio astronomers around the globe on a unique collaboration. If radio telescopes around the world could link up, perhaps they could see the unseeable. General relativity predicted bodies so massive, with such strong gravitation, that not even light could escape from them. They were called black holes, and at first they were regarded as a mathematical anomaly. But evidence mounted suggesting that black holes were more than just a theoretical curiosity. At the center of some galaxies, light far more intense than could be expected from stars has been detected. Massive bodies, such as young stars, attract diffuse matter, which begins swirling and flattens into what's called an accretion disk. Just as planets orbit stars, it's now accepted that galaxies orbit supermassive black holes. The very bright light comes from the accretion disk surrounding the black hole. Matter in the accretion disk is accelerated to incredible speeds, generating intense heat. Along the axis of rotation, jets of ionized material are ejected at close to the speed of light. Computer modeling indicated that the vast energy generated by a black hole's interaction with material in the accretion disk could be detected. The silhouette is the event horizon, the boundary beyond which light cannot escape.
If you want to make a test of the fundamental theories of the universe, you want to go to the most extreme laboratories in the universe, and a black hole is that.
Astrophysicists knew that by linking widely separated radio telescopes, the resolving power of the combined instruments would increase dramatically. The first attempt at imaging the black hole at the center of our own galaxy was made in 2006 using instruments in Arizona and Hawaii. It was not successful, but researchers learned a lot, realizing more telescopes were required. By 2009, an international collaboration between 8 different telescopes had coalesced. They aimed to capture an image of the supermassive black hole at the center of Messier 87.
So for this experiment, it was clear that we need expertise from completely different areas. And so we needed someone with imaging capabilities, we needed someone with numerical relativity capabilities, and in my case, we needed someone who can try to find this additional information via pulsars. And so just being part of this team means you work completely differently.
The project was named the Event Horizon Telescope. Instruments in North and South America, Europe, Hawaii, and even in Antarctica would unite to form a telescope with a virtual diameter equal to the Earth. None of these facilities was designed to work as part of such a large array, and the technical difficulties facing the team were immense. Signals from all the sites would have to be processed at a central location, yet the distances that separated them were so great that a direct line linking them was impractical. Data transfer would take place via computer hard drives that were moved from the place of acquisition to 2 locations, the Max Planck Institute in Bonn and the MIT Haystack Observatory in Massachusetts.
The Event Horizon Telescope collaboration is a collaboration of more than 200 scientists with different backgrounds. They all come from different parts of the world. They have different experiences, different set of skills. These are engineers, observers, theoreticians, and they all work together not only to image the event horizon of a black hole, but also to understand what we're seeing.
Theoreticians already understood that while a black hole could only ever appear as a silhouette, its influence upon light emanating from surrounding matter would be dramatic. By using mathematical simulation, NASA came up with a moving image of what they thought the EHT project would reveal. Viewed from above, the swirling accretion disk appears without distortion. The smooth inner circle is the photon ring, light in orbit just outside the event horizon. When viewed from the side, the black hole's gravitation bends light from the accretion disk so it can be seen from several angles at the same time. But no one really knew what they would see. For decades, evidence had accumulated that a black hole at the center of galaxy M87 was consuming huge amounts of material. Unusually high emissions across the electromagnetic spectrum were detected in this region, and images from the Hubble Space Telescope revealed a huge jet of matter extending out light years. In April 2017, the EHT was scheduled to make a series of coordinated observations of the heart of the M87 galaxy. Each observatory had been equipped with its own atomic clock, as all data had to be meticulously time-stamped. Good weather had to happen simultaneously at each site, and a go, no-go decision was made several hours before each observation. April the 5th, 6th and 7th had good conditions, with data being collected. observations were suspended on the 8th and 9th due to strong winds at the sites in Mexico and Arizona, with the final night's observations made on the 10th and 11th of April.
We have this terrible period of waiting where we don't know if it's all worked. We send all of our data together, and only when it's truly combined do we know if it's worked. And then the even harder part begins of analyzing that data and being very, very careful, doing all the checks and balances to know that we got it right.
During the observation period, 5 petabytes, that's 5,000 terabytes, of data was recorded. The hard drives upon which it was stored weighed half a ton. They were transported to correlators in Westford, Massachusetts, and to Bonn in Germany. While this was relatively simple from most sites, limited access to the South Pole telescope delayed its data for several months. Interpreting radio data as a picture relies upon the black hole's gravitation bending passing electromagnetic waves. The EHT will only be able to see the individual points from rays that are bent toward the Earth. It is the correlation of all these points that builds them into a recognizable image.
Seeing a black hole actually allows us to not only know they exist, and not only know an event horizon exists, it also allows us to test some of the very basic predictions of the theory of general relativity of Albert Einstein, which really describes space and time in its completeness. And that has never been tested before.
In April 2019, the Event Horizon Telescope team released their image of the active center of the M87 galaxy. At its heart was the silhouette of one of the largest black holes we know. It's roughly 38 billion kilometers across, the diameter of our solar system. Its mass is 6.6 billion times greater than our Sun. After predictions flowing from the general theory of relativity more than 100 years ago, the world finally has proof that black holes do exist. But this is not the end for the EHT team. Expanding the number of telescopes in the network will enhance resolution, and there are plans to investigate the black hole at the center of our own galaxy.
The future of this project is amazing. Right? We have done something extraordinary. We've made the first picture of a black hole, but now we want to do even more. Now we want to make the first movie. Now we want to understand how space-time rotates around the black hole. We'll do that by putting more telescopes around the world to make our virtual lens even better.
Investigation into black holes is not restricted to radio astronomy. The New Technology Telescope at La Silla in Chile, the first instrument equipped with active optics, began long-term observation of the stars at the center of our own galaxy in 1992. The NTT observed in the infrared part of the spectrum because only that light was able to penetrate the heavy clouds of gas and dust shrouding the central regions of the Milky Way. A team from the Max Planck Institute plotted the positions of the stars, building up an image of the way they moved. They began using the larger telescopes of the European Southern Observatory at Paranal when they came online. Over 16 years, they mapped the paths of 28 stars.
Well, you see, the Milky Way Center is one of the most important laboratories we have to study in very great detail what's happening in centers of galaxies, in much more detail than we can ever hope to do in all other galaxies. Yet, here we are, we can study whether there's a central black hole, what happens around it, and so forth. All very general issues which you would like to explore and which you cannot really study that much in detail in other galactic nuclei.
Results showed that the stars are orbiting an invisible point, which must be our own galaxy's black hole. Analysis of their highly eccentric paths suggests the Milky Way's black hole is slightly greater than 4 million times the mass of our Sun. Of particular interest is the star S2, which is in a 16-year orbit of the black hole. Its elliptical path was due to take it to its closest pass and its highest speed in April 2018.
Do you want to use it as a tool to test whether general relativity, the theory of Einstein, is actually wrong or right?
General relativity predicts that the black hole's influence would distort S2's light toward the infrared as it reached 3% of the speed of light, which happened, yet another vindication for Einstein. This test is important to researchers because general relativity predicts that time stops inside a black hole's event horizon, and they want to know if the laws of physics break down approaching these extremes. Since Copernicus proposed that the planets orbited the Sun, astronomers have speculated about planets orbiting other stars. Advances in telescope technology allowed researchers to see dips in the brightness of stars that could only be caused by a transiting planet. These fluctuations in intensity gave astronomers clues about the planet's size and its orbit. A different method monitored the spectral shifts in a star's light caused by a consistent change in its position, again only explicable by an orbiting planet. Using these systems, telescopes around the world began cataloguing exoplanets. But the methods used were biased toward finding large planets, similar in size to Jupiter, that had an easily detectable influence on their star. And of all the planetary systems out there, researchers could only use these methods for planetary systems that were edge-on to the Earth. Even so, the number of exoplanets we knew about continued to grow. There were surprises. In 2012, a French team discovered an orphan planet wandering across our galaxy. It had no star. It was detected by its emissions in the infrared. It's difficult to predict the orphan planet's size, but it's certainly still at the very least several times the mass of Jupiter. Naturally, researchers were keen to see Earth-sized planets, planets that could possibly nurture life. When a new and highly accurate spectrometer called HARPS was installed at ESO's La Silla 3.5-meter telescope, this became possible. Among its discoveries are two planets orbiting Gliese 667c, about 20 light-years from Earth. The star is a red dwarf, about 1/3 the mass of our Sun. Of particular interest is Gliese 667c, a planet about 5 times the mass of the Earth, and at a distance from its star that puts it in the habitable zone. Statements about conditions on Gliese 667c have such a large margin of error that much more work needs to be done before it could be declared a possible venue for life as we know it. Another star, 40 light-years away, has a greater range of possibilities. TRAPPIST-1 is an ultra-cool red dwarf star orbited by 7 planets, all of them close to Earth in size. To date, this is the largest number of exoplanets detected orbiting an individual star. At least 3 of the planets are considered in the habitable zone. Many different observatories have been gathering data about the TRAPPIST-1 system, but we still know so little about what kind of environments the different planets might have. However, the coming generation of telescopes should be able to analyze the atmospheres of the TRAPPIST's planets, so they will remain a region of close study into the future. At the moment, around 3,800 exoplanets have been catalogued, and that number continues to grow. In 2018, the satellite TESS was launched to search for more exoplanets. To have a clear view of both the northern and southern skies, TESS was placed in a 14-day orbit around the Earth at a 40-degree angle to the plane of the Moon's orbit. It will systematically map 26 segments of the sky, recording fluctuations in the brightness of nearby stars that reveal exoplanets. During its close passes of the Earth, the Planet Hunter downlinks its data to sites across the United States. Ground-based observatories will then follow up leads in a more detailed way. This type of collaboration between orbiting and terrestrial telescopes is becoming common. An interesting discovery came from the young star Beta Pictoris. Fluctuations in its light did not bear the rhythmic signature of an orbiting planet. Further investigation by the European Southern Observatory revealed 3 comets orbiting the young star. Beta Pictoris is only around 20 million years old and still displays a protoplanetary ring of dust. In TESS's first year of operations, at least 29 new exoplanets were confirmed, with a further 1,000 objects of interest listed in publicly accessible databases. During its 2-year life, TESS will image 200,000 celestial bodies, including 1,000 of the closest red dwarf stars. And there will soon be a new planet hunter in orbit. The Wide Field Infrared Survey Telescope, WFIRST, will use a different technique known as gravitational microlensing to detect much smaller exoplanets. As one star passes in front of another, its gravitation distorts the distant star's light. By monitoring the light over time, a spike in what should be a regular curve reveals an exoplanet orbiting the lensing star. But that's not WFIRST's only objective. There's a gap in knowledge that some cosmologists find embarrassing. When quantifying the speed at which galaxies rotate and the amount of mass they contain, there's a baffling mismatch. Our laws of physics say that spinning galaxies do not contain enough matter, and therefore enough gravitation, to prevent them from flying apart. And yet, they don't. Astrophysicists came up with the dark matter hypothesis. This is not just matter that doesn't glow. It is matter that interacts with nothing else. The only influence it has is via gravitation. Halos of dark matter surrounding galaxies is the current method to explain why they move the way they do. Estimates say there is 5 times more dark matter than matter, yet no one can explain it. Another fascinating anomaly is that early galaxies, galaxies whose light has taken more than 10 billion years to reach us, rotate at a slower rate. The influence of dark matter is not as pronounced. New generations of telescope are being built to help researchers answer some fundamental questions about the laws governing the universe. But it seems that cosmology has reached a stage where it is just discovering how little we know about what lies beyond the solar system. The space industry is at a turning point. NASA's Space Launch System is about to fly. With it, the new Orion spacecraft, a collaboration between NASA and ESA, will target the Moon. A landing is scheduled for 2024. As far as the United States is concerned, low Earth orbit is now the province of corporations, with Boeing and SpaceX competing to break Russia's stranglehold on manned trips to the International Space Station. New technology is cutting costs and increasing launch frequency, with complex satellites being so small they can be deployed in new ways. Several companies are working towards space tourism. Virgin Galactic says its promised trips beyond the atmosphere should start happening soon. Since the retirement of the shuttle in 2011, space science has shifted focus to research carried out on the International Space Station and to robotic missions in deep space. During this period, all manned flights have been to and from the ISS, with the only viable spacecraft being the Russian Soyuz. This has cost both NASA and ESA billions in launch fees. Russia, Europe and Japan, major partners in the ISS, developed their own cargo craft to resupply the space station. But NASA tendered for private companies to take on these responsibilities. Rising star in the launch business, SpaceX, was contracted to develop a cargo craft that would launch on its Falcon 9 rocket.
3, 2, 1, 0. And launch of the SpaceX Falcon 9 rocket as NASA turns to the private sector to resupply the International Space Station.
A second aerospace business, Orbital Sciences Corporation, now Orbital ATK, signed a contract for similar hardware and services. NASA is developing its own launch system and the Orion spacecraft, but it's designed for missions far more ambitious than resupplying the ISS. America's activity in low Earth orbit is being reallocated to the commercial sector, and NASA is helping with technology transfers. Agency administrators want two completely different systems, giving the space agency what they call dissimilar redundancy. When the space shuttle twice suffered catastrophic failures, NASA was stuck on the ground for years while exhaustive investigations were made. The redundancy approach will prevent this paralysis. In 2014, NASA signed contracts with Boeing and SpaceX to develop and test human-rated spacecraft to ferry astronauts to and from the International Space Station. It was a continuation of the dissimilar redundancy approach. The space agency has set performance criteria for the new craft and crew training, but is taking a hands-off approach regarding how the companies meet the requirements. Boeing's spacecraft is called the Starliner. It has space for 7 astronauts and will be capable of being used 10 times. NASA requires any human-rated spacecraft to meet higher standards of safety and reliability than a cargo craft, and new capsules must demonstrate, via a series of test flights, that they meet certification. One crucial part of the new spacecraft is the launch escape system. It's the equivalent of a fighter pilot's ejector seat. Both Boeing and SpaceX have opted for a new method of capsule-mounted rockets to push the craft clear in an emergency, in contrast to the more traditional escape tower above the agency's new Orion spacecraft. The trial of Boeing's escape system worked well, with the exception that only 2 of the 3 parachutes deployed, but the problem is understood. The Starliner could continue to the next uncrewed launch to orbit. One of the novel features of Boeing's capsule is its ability to return to dry land, like Russia's Soyuz craft. Airbags, stowed behind the heat shield, inflate prior to landing. Without the need to deploy ships for an ocean recovery, there will be considerable savings. Though the capsule can fly on the Delta IV, the Falcon 9, and the yet-to-be-flown Vulcan, initial testing of the spacecraft has been with the Atlas V launcher. The Atlas ground support infrastructure has been modified to accommodate the Starliner with the addition of a crew access arm. The Starliner made its first unmanned test flight in December 2019. Its destination was the ISS. The launch was perfect, and 4.5 minutes after liftoff, the first stage separated. Next, the boost protect covers and the aeroskirt were jettisoned, and the Centaur upper stage burned for a further 7 minutes, following the course parameters perfectly. After separation, the capsule was in a suborbital trajectory, selected because it allowed a safe path back to the ground in case of a malfunction during the boost phase. To achieve the correct orbit, the craft was required to fire its 4 attitude and orbital maneuvering thrusters 31 minutes after liftoff. However, the Starliner's sequence clock was incorrect, and the orbit insertion burn did not happen. Ground control was able to salvage parts of the mission, but the craft was not able to reach the International Space Station. This setback will delay the Starliner's first mission carrying astronauts. SpaceX's Crew Dragon capsule is a refinement of the cargo craft that first flew in 2010. From the beginning, the Dragon capsule has had a heat shield, enabling it to return safely to the ground. No other ISS cargo craft has had this ability. In addition, the Dragon also has a window. This should have been a clue to SpaceX's long-term plans for the craft. In 2014, after the contract for a human-rated craft was signed, SpaceX began work on the Dragon 2. Like its Boeing equivalent, the Dragon 2 sits above a service module that can carry unpressurized cargo and includes a heat exchange unit and a coating of solar cells that does away with the moving parts involved in extendable solar wings. The Dragon 2 can accommodate 7 astronauts, though NASA has said it will generally only send 4 people at a time. Control interface is via a touchscreen. Cape Canaveral's Launch Complex 39A has been equipped with a crew access arm, and in March 2019, in a flight known as Demo 1, the unmanned craft made its first spaceflight. The Dragon carried a dummy astronaut wired with sensors to monitor G-forces and a small delivery of equipment for the ISS. The launch and the phasing maneuvers to align its orbit with the ISS were all correctly executed. The automated docking procedure went smoothly, and the Dragon stayed connected to the space station for 5 days. Decoupling from the ISS went as expected, and observers on the ground were delighted with the capsule's behavior. Throughout the mission, every aspect of the Dragon 2's performance was monitored. The craft's return to Earth was faultless, and the recovered capsule would be reused for the one remaining uncrewed flight test. SpaceX planned to use new capsules for manned flights and then recycle the craft for cargo use. Confident planners at SpaceX and NASA were looking toward the first crewed flight. The final certification test was an in-flight simulation of a booster failure that would monitor the Dragon's launch escape system. But before that, the craft's Super Draco engines, used in mission aborts, needed retesting. This was considered routine and had been carried out many times. A leaked video revealed an explosion that had destroyed the capsule. The problem was not engine failure, but a faulty valve. The flight test of the Dragon 2's escape system eventually happened early in 2020. But just as with the Boeing capsule, which was also well behind schedule, the explosion and the inquiry that followed were another unwelcome delay.
2, 1, 0. Ignition.
Of maximum dynamic pressure, the core stage's engines were cut and the escape system triggered automatically. Shortly after, aerodynamic stresses on the tumbling booster caused it to explode.
Cheering in the room, and bright flash there. It looks like that maybe Falcon 9 breaking up.
The certification test was a success, and the Dragon 2's next flight will carry astronauts. But there is another spacecraft in development that's worth mentioning, the Sierra Nevada Corporation's Dream Chaser. It's a lifting body craft designed to ride to orbit on an Atlas V, but return to the ground via a commercial landing strip. So far, the Dream Chaser's only flights have been glide tests. As a cargo ship, the Dream Chaser can return a 1,750 kilogram load to the surface. As a crewed vehicle, it is designed to take from 2 to 7 astronauts. The European Space Agency has shown interest in the craft, with the possibility of launching European astronauts atop of French Ariane. The craft will use the bipropellants methane and hydrogen tetroxide for on-orbit maneuvers, doing away with the highly toxic hydrazine. When the space shuttle landed, it had to be at a restricted runway where suited ground staff purged the craft of residual hydrazine. Originally in the running for a NASA contract for ferrying astronauts to the ISS, it missed out because Sierra Nevada could not comply with NASA's 2017 deadline for crewed missions. The favored contractors, Boeing and SpaceX, both failed to meet that same deadline. But the Dream Chaser has a contract for cargo missions to the ISS, and an expendable cargo module known as Shooting Star is being developed. The company still plans a human-rated version of the Dream Chaser, but it's unclear when the craft will fly. Cape Canaveral's Launch Complex 17 was the starting point for many historic Delta II missions. Since the demise of the Space Shuttle, NASA infrastructure from the earliest days of spaceflight has been eliminated. Since the heady days of the space race, NASA's budget has been steadily trending downward, and various launch sites have been given over to the private sector. While NASA has been overseeing the commercial craft that will continue to service the research work carried out on the ISS, its sharpest focus has been on the new Orion spacecraft and the giant space launch system that will boost it to orbit. After its establishment in 1958, the agency's challenge had been to master space technology and then to reach the moon. But since then, the exploration side of NASA's charter has been achieved by robotic missions. Now, a new plan called Artemis will return to the moon. It relies upon the Orion spacecraft and the SLS. The Space Launch System will be the most powerful rocket yet built. And although the design features the latest technologies, most of its components are derived from the Space Shuttle. The Block 1 version, which will send an unmanned Orion spacecraft to orbit the moon, features a central core that owes much to the shuttle's external tank. At the base of the central core are 4 RS-25 engines. The shuttle had 3 of these engines, and NASA still has 16 left over from the shuttle program. Although the engines remain the same, their control systems have been redesigned. Each one has been exhaustively tested, and when the original batch have been utilized, an upgraded version, the RS-25D, will be available. Flanking the central core of the Space Launch System are two solid fuel boosters. Again, a refinement of shuttle technology, but with each booster having 5 instead of 4 segments. The new design has been rigorously tested. The boosters will only burn for the first 2 minutes of flight, each consuming 6 tons of propellant every second and providing more than 75% of the rocket's thrust. Unlike the shuttle's boosters, these will not be reusable. The upper stage for the Block 1 configuration of the Space Launch System is called the Interim Cryogenic Propulsion Stage, the ICPS. It's a stopgap modification of the Delta Cryogenic Second Stage, used with the Delta 3 and 4 launchers. In 2014, a Delta IV fitted with this upper stage lifted an Orion spacecraft to its first orbital test. The Orion, with a dummy service module, was boosted to a height approaching 5,800 kilometers, allowing it a high-speed return to Earth similar to a lunar mission. The much larger exploration upper stage was to replace the ICPS for the first crewed mission atop a Block 1B launcher. But design changes have led to delays, and the EUS now won't fly till the 4th Orion mission. The Orion spacecraft itself will comfortably accommodate 4 astronauts for 21 days, with the crew breathing air at atmospheric pressure. The craft is intended for missions beyond Earth orbit. It's designed to integrate with larger modular structures such as habitation modules, specialist landing craft, or the planned lunar gateway. Instrumentation and the control interface are primarily via a touchscreen. The digital control enables weight saving through the absence of wires and switches. The Orion Service Module is the European Space Agency's contribution to the craft. It's derived from the automated transfer vehicle which delivered cargo to the ISS. Oxygen and nitrogen cylinders in the service module supply air. There's a water storage tank, and wastewater is not dumped but recycled. A 4-wing solar array generates 11 kilowatts for battery charging and powering the electrical subsystems. For propulsion and maneuvering, the service module is equipped with a version of the same system used by the Space Shuttle. But like so many aspects of this spacecraft, the system can be easily replaced when alternate models under consideration become available. The third important piece of the Orion craft is the launch abort system, mounted above the capsule. 3 different types of solid fuel rocket are designed to fire at the first hint of a malfunction in the launcher.
1. Ignition.
The system was tested in July 2019 above a Minotaur booster, a highly modified Peacekeeper missile. Engineers were delighted with its performance. Launch infrastructure is being upgraded for the SLS, and there's increased activity in preparation for the first test of the big new rocket. There were celebrations as the core stage left the Michoud assembly facility. But it hasn't gone to Cape Canaveral, not yet. It was taken by barge to the Stennis test facility in Mississippi, where the stage will be powered up for a series of tests known as the Green Run test campaign. The date, or even the year, for the first launch has been put back a number of times, although it could be as early as 2020. NASA's Exploration Initiative received a jolt in 2019 when US Vice President Pence, the chairman of the National Space Council, called for NASA's Exploration Initiative to be accelerated.
It is the stated policy of this administration and the United States of America to return American astronauts to the moon within the next 5 years. And now's come the time for us to make the next giant leap and return American astronauts to the moon, establish a permanent base there, and develop the technologies to take American astronauts to Mars and beyond.
The existing plan had called for a moon landing no earlier than 2028. The month after the Vice President's speech, NASA announced the Artemis program, Artemis being the sister of Apollo. Late in 2019, companies were called to tender for a lunar lander and for a lunar space station known as the Lunar Gateway. The timeline calls for Artemis 1, an uncrewed Orion craft, to enter a series of looping orbits of the moon in 2020. Astronauts are in training for Artemis 2, due to launch in 2022. The current proposal will see a crew of 4 sent to a retrograde orbit of the moon in a flight that could last as long as 21 days. The powerful exploration upper stage will not be ready for this flight, and its proposed trajectory has been modified to accommodate the limited capacity of the interim cryogenic upper stage. During this time, the Artemis plan calls for commercial launch services to make a series of uncrewed flights to position elements of the Lunar Gateway and Lunar Lander in orbit around the moon. A contract has been signed with Maxar Technologies for a power and propulsion element. Some see this phase of the Artemis program as a weak link, because the US Congress has been reluctant to authorize additional funds. There are no concrete blueprints for a lunar lander yet, and some have suggested that the 2024 deadline is being pushed too enthusiastically. Artemis 3 will see a male and a female astronaut land near the lunar South Pole, where ice exists within permanently shaded craters. Long-term goals for NASA's Space Exploration Initiative include the development of technologies that will enable a landing on the surface of Mars. Finally, a different form of spacecraft will soon be taking passengers. Virgin Galactic will start taking paying customers to space in 2020. Everything about the company's spaceships, Enterprise and Unity, is reusable, and Virgin is building 2 additional spacecraft. Passengers will experience weightlessness for about 6 minutes. Virgin is also entering the satellite business with a launcher service using a 747 called Cosmic Girl, acting as an air launch mothership.